In December of 1995, a group of astronomers pointed the Hubble Space Telescope at a patch of sky roughly the size of a grain of sand held at arm's length. It looked empty. No stars, no galaxies, nothing in normal exposure would even register. They left the shutter open for 10 straight days anyway. What came back should not have been possible. Roughly 3,000 galaxies packed into that single dark speck, each one containing billions of stars of its own. Not 3,000 stars, 3,000 entire galaxies, most of them older than our sun, some of them so distant their light had been traveling since before Earth had an atmosphere worth breathing. Sit with that for a second. Pick any point in the night sky you have ever ignored. The gap between two visible stars, the smudge you assumed was a smear on your window. Statistically, that nothing is full. Full in a way the human eye was never built to register and the human mind was never built to hold. We're going to spend the next several hours with the people who tried to close that gap. Not the finished textbook version of astronomy, with its clean diagrams and confident dates, but the actual, stumbling, centuries-long argument between what the sky appears to be and what it is. It starts, as most human obsessions do, with something much smaller and much more desperate than a galaxy. It starts with a person trying not to starve. Long before anyone asked what a star was made of, someone needed to know, with total certainty, when the rains would come, when the herds would move, when the cold would arrive. Getting the sky wrong did not mean an interesting philosophical error. It meant a dead season. That is where this story actually begins. Not with genius, with counting. And the counting, it turns out, is older and stranger than almost anyone expects. The Hubble Deep Field was not an easy sell inside the astronomy community. Telescope time is precious, rationed, fought over by scientists with specific, funded projects. Spending 10 full days staring at what appeared to be an empty patch of sky, with no guarantee of anything useful coming back, struck some colleagues as reckless, even wasteful. Robert Williams, the director of the Space Telescope Science Institute at the time, made the call anyway, using his own discretionary observing time to gamble on the emptiness. He later said the goal was simply to see what was there, not to prove a theory, just to look longer and harder than anyone ever had at one single, unremarkable point. The gamble worked in a way almost nobody fully anticipated. Nearly every point of light in that image, once analyzed, turned out to be an entire galaxy rather than a single star. Some of that light had been traveling for over 10 billion years, meaning the documentary is not describing what those galaxies look like now. It is describing light that left its source before our own sun had finished forming. That single fact tends to break people's sense of scale the first time they actually absorb it. You are not looking at a photograph of the universe as it currently exists. You are looking at a photograph of history, layered thousands of times over, each galaxy a different, older slice of the past, arranged next to each other purely by coincidence of geometry. This documentary is going to keep returning to that same disorientation over and over in different forms. The gap between what a glance tells you and what patient, careful measurement eventually reveals. It is the single idea underneath every chapter that follows, and it began, as we said, with something far more modest than a space telescope. There have been deeper fields since. The Hubble Ultra Deep Field in 2004 stared even longer and even smaller patch of sky and found nearly 10,000 galaxies packed into it. The Hubble Extreme Deep Field in 2012 combined years of accumulated exposure time into a single image. Each new attempt did not shrink the mystery. It simply confirmed that the first result was not a fluke, was not an accident of pointing the telescope at an unusually crowded patch by chance. That repeatability matters enormously to how seriously scientists take a result. Point the telescope anywhere else, at any other seemingly empty patch of sky, and roughly the same density of ancient galaxies turns up. The implication is almost too large to comfortably hold. Multiply that single tiny patch across the entire visible sky, and current estimates place the number of galaxies in the observable universe somewhere north of 100 billion, possibly closer to 2 trillion. It is worth being precise about how the Hubble Deep Field was actually chosen, because the choice itself tells you something about how careful this science really is. Astronomers deliberately selected a patch near the North Celestial Pole, an area the telescope could observe continuously without the Earth or Moon blocking the view, and one that had already been checked to avoid bright foreground stars or known nearby objects that might contaminate the exposure. Even the emptiness had to be engineered. Skeptics within the astronomical community at the time worried the whole exercise would simply confirm what everyone already assumed and add nothing new. A famous piece of scientific caution, worth remembering whenever a field feels settled. The people closest to a discovery are frequently the ones most confident nothing further remains to be found there, right up until the moment the instrument proves them wrong. There's a specific number worth holding on to as we move backward in time from here, away from Hubble and toward tally marks on bone. If the entire history of the universe were compressed into a single calendar year, with the Big Bang occurring at the first second of January 1st, modern humans would not appear until roughly 11 o'clock at night on December 31st. Written astronomy would occupy only the final seconds before midnight. Consider, too, the sheer mechanical patience the original 1995 exposure demanded from the telescope itself. Hubble orbits Earth roughly every 97 minutes, meaning the planet itself repeatedly passed between the telescope and its target during that 10-day exposure. Engineers had to break the observation into hundreds of separate shorter exposures, taken across dozens of orbits, then painstakingly aligned and combined afterward into the single continuous image the public eventually saw. That stitching together of fragments across time is, in a strange way, a fitting metaphor for how this entire history has been assembled. No single observer, no single instrument, no single lifetime produced the picture we now hold of the universe. It is a composite built from thousands of separate, imperfect exposures taken across cultures and centuries, aligned only slowly, and only by people willing to trust the pattern emerging underneath all that scattered individual effort. There is a final thought worth carrying forward from this opening chapter before we travel backward into deep time. Every civilization that appears in the hours ahead believed, at some point, that they had essentially finished the job of understanding the sky. The Babylonians believed their eclipse tables were close to complete. Ptolemy believed his geometry was final. Newton believed gravity explained essentially everything worth explaining about the heavens. Each one was working with the best possible tools of their moment, and each one was, in some important way, still standing at the very beginning of a story none of them could see the full shape of yet. There's a specific number worth sitting with a little longer, because it captures the disorientation better than any description can. Of the roughly 3,000 galaxies visible in that original 1995 image, astronomers estimate the light from the very faintest of them had already been traveling for around 12 billion years by the time it finally struck the telescope's mirror. 12 billion years is not simply a long time. It is close to the entire age of the universe itself, meaning some of that light began its journey when the cosmos was still, relatively speaking, young. It is worth remembering, too, that this documentary is not simply a list of facts arranged by date. It is an argument about how confidence itself behaves over time, how each generation's certainty gets quietly revised by the next, and how that revision has never once stopped, not for the Babylonians, not for Ptolemy, not for Newton, and almost certainly not for us. Keep that argument in mind as we go all the way back now, past written history entirely, to the very first known attempt to keep track of anything in the sky at all. There is one more number worth carrying into the rest of this documentary, because it will keep resurfacing in different forms across every chapter ahead. Light itself is not instantaneous. It travels at a fixed, finite speed, roughly 186,000 miles every single second, fast beyond ordinary human intuition, and yet still far too slow to outrun the sheer scale of the universe it moves through. Every single image this documentary will show you of a distant star, a nebula, or a galaxy is not a picture of that object as it exists right now. It is a picture of the past, sometimes the very distant past, arriving late, the way a letter from someone long gone can still turn up decades after it was written. Hold on to that image of a grain of sand held at arm's length. We will return to it deliberately at the very end of this documentary, and it will mean something noticeably different by the time we get there, once you have sat through everything that came before it. None of what follows is a simple march of progress from ignorance to enlightenment, tidy and inevitable. It is stranger than that, full of dead ends, lucky accidents, personal grudges, and long stretches of quiet, unglamorous waiting. It is, in other words, a genuinely human story, which is exactly why it deserves to be told slowly, in the dark, the way any story worth staying awake for should be told. That is where we begin properly now, not with a telescope, with a bone, a blade, and someone in the dark who could not afford to be wrong. There's a small piece of baboon fibula found in a cave in the Lobombo Mountains on the border of modern Eswatini, notched with 29 distinct marks. It is roughly 43,000 years old, 29 marks, the length almost exactly of a lunar cycle. Nobody can prove with total certainty what it meant to the person who cut it. Maybe it was a calendar, maybe it was something else entirely, and we are projecting our own hunger for pattern onto a piece of bone. But the marks are consistent, grouped, deliberate. Someone was tracking something in the sky, night after night, and refusing to let it slip. Consider what that actually required. No writing system existed yet. No numerals, no shared vocabulary for what a phase or a cycle even was. Just a person, alone in the dark, holding a count in their head across nights they could not simply write down and check later. And the cost of getting it wrong was not embarrassment. It was timing a migration a week too early and starving on the trail. It was misjudging the flood season and losing the harvest. The moon was not poetry to these people. It was infrastructure. This is the part of astronomy's history that almost never makes it into the popular version. No templis, no telescopes, no triumphant discovery. Just quiet, repetitive, unglamorous attention, paid across generations, to something moving predictably overhead while everything on the ground refused to be predictable at all. It is fragile knowledge, too. A single skipped night, a single forgotten mark, and the whole record breaks. And yet it survived, passed down, refined, eventually formalized, until entire civilizations built their calendars, their religions, their agriculture on top of what began as scratches on a dead animal's leg bone. By the time actual cities rose along the Tigris and Euphrates, that instinct, the refusal to lose count, had become something closer to a discipline. And in Mesopotamia, that discipline was about to be handed over to people with something the bone counters never had: writing, mathematics, and the patience to keep records for 7 centuries without stopping. Compare the Lobombo bone, briefly, to something found later and further north, in what is now the Dordogne region of France. The Ishango bone, discovered along the Nile in the 1950s and dated to somewhere between 18 and 20,000 years old, carries similarly grouped notches, and researchers have argued, with less certainty than headlines usually suggest, that these two may track a lunar cycle rather than simple hunting tallies. The honest scholarly position is more cautious than the popular one. We cannot interview these people. We cannot ask them directly what the marks meant, whether they were counting days, counting kills, counting something entirely lost to us. What survives is only the pattern, and the pattern keeps landing suspiciously close to 29 or 30, the length of a lunar month. What is not in dispute is the underlying behavior. Long before agriculture, before permanent settlement, before anything resembling a city, some humans were already treating the sky as data. Not myth first, data first. The stories, the gods, the omens, those came later, layered on top of a much older, colder habit of simply counting what repeats. It is tempting, looking back from a position of total astronomical confidence, to treat this era as primitive. Resist that. A person with no writing system, no shared numerals, no way to check their work against anyone else's, held a running count of a 29-night cycle in their own memory, correctly, often enough that the habit survived long enough to get carved in a bone and buried by time, until archaeologists found it tens of thousands of years later. There is a broader pattern worth naming before we leave this chapter behind, because it sets up almost everything that follows. Every civilization that later formalized astronomy, Babylon, Egypt, China, the Maya, independently arrived at lunar and solar tracking as a foundational technology, almost never as an afterthought. It suggests something close to a universal human pressure, not a cultural accident. Wherever people needed to plan seasons and survival with any precision, the sky became the first reliable clock available to them. There is an unglamorous, practical detail worth adding here, because it grounds the abstraction in something physical. A lunar month is not a clean 29 or 30 days. It averages roughly 29.5 days, meaning any tally system based on whole numbers has to periodically adjust, skip a mark, add an extra one, or simply accept a small, accumulating drift. Whoever cut these ancient marks was already, in some crude sense, wrestling with the same messy irregularity that would frustrate astronomers for millennia afterward. Compare this fragile, individual record keeping to what agriculture would eventually demand. Once humans stopped following herds and started planting fixed fields, the cost of a miscounted season multiplied enormously. A hunter who misjudged the moon by a night might miss a migration. A farmer who misjudged the solar year by even a handful of days could lose an entire harvest for an entire settled community. The stakes of getting the sky right did not shrink with civilization. They grew. It is worth acknowledging directly how much uncertainty still surrounds these earliest artifacts, rather than smoothing it over for the sake of narrative. Some archaeologists argue the notch groupings on bones like the Ashango artifact more plausibly represent simple counting or a rudimentary number system unrelated to lunar tracking at all. The lunar interpretation is compelling, widely cited, and far from proven beyond doubt, a genuine reminder that even the very first chapter of this story rests partly on informed, careful guesswork. Whatever the precise intention behind these specific bones, the broader pattern across the archaeological record is harder to dispute. Structures like Stonehenge, built in stages beginning around 3000 BCE, and earlier still, sites like Göbekli Tepe in modern Turkey, dated to roughly 9500 BCE, show clear evidence of deliberate alignment with solstices and celestial events, proof that organized, communal sky watching predates writing by thousands of years across multiple, unconnected regions of the world. It is also worth noting how differently various early cultures approached this same basic problem of tracking the sky, since the diversity itself is instructive. Ancient Egyptian priests, watching the annual pre-dawn rising of the star Sirius, used it to predict the Nile's life-giving flood with such reliability that they built their entire calendar around that single stellar event. On the opposite side of the world, without any possible contact or shared influence, Maya astronomers in Mesoamerica independently developed extraordinarily precise calendars tracking Venus's cycle, accurate to within a fraction of a day across centuries of observation, arriving at broadly similar conclusions about the value of celestial patience through completely separate paths. It is worth adding a final grounding detail before we leave this era behind. The particular bone chosen for the Lubombo artifact, a baboon's fibula, was not an arbitrary or accidental material. Bone tools of various kinds were common throughout this period, but the deliberate selection of a smooth, easily notched surface for a repeated, careful counting task suggests intention rather than idle scratching, a purpose-built object rather than a random discard picked up and marked on a whim. The transition out of this era into the organized river valley civilizations that would formalize sky watching into an actual institution did not happen quickly or uniformly. Thousands of years separate the Lubombo bone from the first Babylonian clay tablets, an enormous stretch of time during which similar quiet, individual observation was almost certainly happening across dozens of unrecorded cultures, most of it lost entirely, leaving only the rare, durable fragments like this one to hint at everything else we will never know about. It is worth adding one more small, grounding thought before this chapter closes for good. Whoever notched that bone in the Lubombo Mountains 43,000 years ago almost certainly never imagined their small, private act of counting would survive them by hundreds of centuries, let alone that it would open a documentary about the entire history of a discipline that did not yet have a name. There's something quietly moving in that, a private, unglamorous habit outlasting every civilization, every language, and every belief system that came after it, simply because someone once refused to lose count. Keep that image of a single person, alone, counting the moon under an open sky, somewhere in your mind as we move forward. Every observatory, every telescope, every satellite covered in the chapters ahead is, in a very real sense, simply a larger, more elaborate version of that exact same act. It would be centuries, plural of centuries, before anyone formalized what this quiet counting eventually became. But the instinct itself, watch, remember, do not lose the pattern, never really went away. It simply kept getting handed forward, generation after generation, waiting for civilization to finally give it writing, mathematics, and institutions large enough to carry it properly. It is a strange kind of intimacy, honestly, imagining that specific person alone in the cold, doing something so ordinary and so essential at once. No audience, no record beyond the marks themselves, just a private, nightly negotiation with an uncertain sky. Around 750 BCE, in the temples of Babylon, scribes began doing something no one had sustained before. They wrote down every single night exactly where the moon and planets sat against the stars. Not for one lifetime, for generation after generation, on clay tablets baked hard enough to survive war, flood, and roughly 2,500 years. This is where astronomy stops being memory and becomes archive. A single scribe's lifetime of observation is interesting. 700 years of continuous, cross-referenced observation is something else entirely. It is a machine built out of patient, mostly anonymous men, each one adding a few decades to a project none of them would live to see finished. Out of that archive came the Saros cycle, the discovery that eclipses repeat in a pattern roughly every 18 years, 11 days, and 8 hours. Get that number right, and you can tell a king with total confidence that the sun will go dark on a specific evening years before it happens. Try to imagine what that meant to the people watching. An eclipse, unpredicted, looks like the end of the world. An eclipse, predicted months in advance and announced by a priest standing calmly in front of a crowd, looks like something closer to power. That gap between panic and prediction is where astronomy first became useful to empire. But underneath the political theater was something quieter and more remarkable. These scribes were not reasoning from a theory of what the universe was made of. They had no model of orbits, no concept of gravity, nothing we would recognize as physics. They were doing something closer to pure pattern recognition at a scale and duration that still, honestly, sounds slightly insane. 700 years of nightly records. Think about what does not survive 700 years. Empires do not. Languages barelido. And yet somewhere in Babylon, this one specific habit, watching the sky and writing it down, outlasted the people who started it by dozens of generations. This is astronomy's first quiet miracle, and it rarely gets mentioned outside of specialist journals. No named genius, no single eureka moment, just an institution that decided the sky was worth watching forever and meant it. The Babylonian system was not purely descriptive either. Around the 5th century BCE, astronomers in Babylon developed one of the earliest systematic zodiacs, dividing the sky along the sun's apparent path into 12 equal segments, a framework that Greek astronomy would later inherit almost wholesale, and one that still structures how astrologers, if not astronomers, describe the sky today. It is worth being honest here about the blurred line running through this entire chapter. Babylonian astronomy and Babylonian astrology were not separate disciplines the way we treat them now. The same scribes who tracked eclipses with genuine mathematical rigor also produced omen texts, reading planetary positions as signs about a king's fortune or a coming harvest. Prediction and superstition sat in the same institution, often in the same document. That mixture is not a flaw in the story. It is the story. Science did not arrive fully separated from superstition, gift-wrapped and labeled. It grew up tangled inside it, gradually, unevenly, with the predictive mathematical core slowly proving itself useful enough to survive long after the omen reading around it had faded into a historical footnote. Consider also what Babylonian astronomy specifically got right about planetary motion using nothing but arithmetic, no geometry at all in its earliest forms. Their method, sometimes called the zigzag function, tracked a planet's changing speed across the sky as a repeating pattern of linear increases and decreases, essentially treating a smooth curve as a jagged approximation built entirely from straight lines and simple addition. It is a strange, almost brutalist way to model the heavens, and it worked remarkably well for practical prediction. It is worth naming a specific Babylonian astronomer whose work survives in unusual detail. Navigators, working sometime around 500 BCE, and later Kadinu, working roughly 2 centuries after him, produced increasingly refined mathematical schemes for predicting lunar and planetary motion, schemes precise enough that some of their calculated values for the length of the synodic month differ from modern measurements by only a fraction of a second. That level of precision, achieved with nothing but eyesight, patience, and generations of accumulated arithmetic, deserves to be said again plainly. A fraction of a second of error across a measurement made without any mechanical clock, without any lens, without any instrument beyond a straight sighting tube and a very long institutional memory. It remains one of the most quietly astonishing achievements in the entire history of this documentary. Greek astronomers who later inherited this Babylonian data, including the mathematician Hipparchus in the 2nd century BCE, did not simply copy it. Hipparchus used centuries of Babylonian eclipse records, combined with his own careful observations, to discover the precession of the equinoxes, the extremely slow wobble of Earth's rotational axis, a cycle so long, roughly 26,000 years, that no single human lifetime could ever have detected it through direct observation alone. The physical clay tablets themselves deserve a closer look, because their survival is almost as remarkable as their content. Unlike papyrus or parchment, which decay readily, sun-baked or kiln-fired clay proved extraordinarily durable, and thousands of these astronomical diaries, some fragments spanning single nights, others summarizing decades, have been recovered from the ruins of Babylon and nearby sites. Painstakingly translated by modern Assyriologists working from cuneiform script that took its own long process of rediscovery to decipher. It is worth remembering the institutional structure that made this centuries-long project possible in the first place. These were not independent hobbyists. Astronomer priests operated within organized temple bureaucracies, with observational duties passed formally from teacher to student, generation after generation, embedded within a religious and administrative system that treated accurate sky watching as a core function of the state itself, not an optional intellectual pursuit. It is worth adding one more concrete illustration of exactly what Babylonian mathematical astronomy could accomplish, because the specific numbers still hold up remarkably well under modern scrutiny. Their calculated value for the length of the synodic month, the time from one new moon to the next, came out at 29 days, 12 hours, 44 minutes, and roughly 3 seconds. Modern measurement puts the true value at 29 days, 12 hours, 44 minutes, and about 2.8 seconds. A discrepancy of a fraction of a second, achieved with nothing more than eyesight, clay tablets, and several centuries of uninterrupted institutional patience. It is worth adding a final human detail to close out this chapter properly. These Babylonian astronomer priests were not anonymous in every case. Some scribes signed their tablets, leaving behind names, family lineages, and even occasional personal complaints about difficult working conditions or disputes over pay, scratched into the margins of otherwise rigorous astronomical data. Even inside an institution built around multi-century patience, individual, specific, irritated human beings were doing the actual nightly work. That detail matters more than it might first seem. It is easy, looking back across 7 centuries of institutional record-keeping, to imagine the whole project as something impersonal, almost mechanical in its consistency. It was not. It was built one shift at a time, by specific tired people, climbing to a rooftop night after night, year after year, trusting that their small nightly contribution would eventually add up to something none of them would live long enough to fully appreciate. It is worth adding a closing thought that connects this chapter directly to everything still ahead. The Babylonians proved something that the rest of this documentary would spend the following 2,500 years repeatedly rediscovering in new forms, that the sky, however chaotic it appears on any single given night, contains real, extractable, mathematical order underneath, provided someone is willing to watch closely enough, for long enough, without giving up partway through. Hold on to this specific idea as we move forward in Greece. Patient, sustained observation, on its own, without any theory attached, can already get you remarkably far. What Greek astronomy would add next was not more patience. It was an attempt to explain why the patterns existed in the first place. It is worth remembering, as this chapter closes, exactly what made this Babylonian achievement so different from everything that came immediately before it. This was not one gifted individual noticing a pattern. It was an entire culture deciding deliberately that watching the sky was worth doing forever and building the institutions necessary to make forever an achievable goal rather than an empty promise. The Greeks inherited the Babylonian data and asked a question the Babylonians mostly had not. Not just where will the planets be, but what shape is the machine that puts them there? Around 380 BCE, Eudoxus of Cnidus proposed an answer. Nested, invisible crystal spheres spinning around the Earth, carrying the sun, moon, and planets with them. It was elegant. It was also, in its early form, wrong enough that the planets simply did not move the way the spheres predicted. Mars, in particular, was a problem. Sometimes it slows down, stops, and appears to move backward against the stars for weeks before resuming its normal path. Perfect circles cannot explain that. Something else was needed. The fix arrived slowly, refined across centuries, and reached its final and most influential form around 150 CE, in the work of an astronomer in Alexandria named Claudius Ptolemy. His book, later known by its Arabic title the Almagest, added circles riding on circles. Epicycles. A planet does not simply orbit the Earth. It traces a small loop while that loop itself orbits the Earth. It is, by any honest measure, a strange and ugly piece of machinery. And it worked. Ptolemy's model predicted planetary positions accurately enough that astronomers used it, almost without serious rival, for the next 1,400 years. That length of time is worth sitting with. 1,400 years is longer than the entire span from the fall of Rome to today. An entire civilization's worth of astronomers grew up, studied, taught, and died, all working inside a model of the universe that placed a stationary Earth at the exact center of everything that existed. And here is the part that should genuinely unsettle you. The model was not obviously broken. It kept working, more or less. Astronomers could add another epicycle here, adjust another circle there, and the predictions would hold. Wrongness, it turns out, can be endlessly patched if you are willing to make the machinery ugly enough. That is the trap this chapter is really about. Not ignorance. Competence misapplied for over a millennium, because a system that produces correct predictions gets mistaken for a system that describes reality. It is a mistake astronomy would make more than once, and it would take something close to a revolution to finally break the habit. It is worth naming exactly how the equant, one of Ptolemy's more controversial tools, actually worked, because the cheat itself is fascinating. Rather than having a planet move at constant speed around a perfect circle centered on the Earth, Ptolemy placed the Earth off-center and then measured the planet's speed as if viewed from yet a third, entirely imaginary point. It produced accurate predictions. It also violated the ancient principle that heavenly motion had to be perfectly uniform and circular, a contradiction some later astronomers found deeply uncomfortable. That discomfort matters. It means the flaws in Ptolemy's system were not hidden from serious scholars for 1,400 years. They were visible, debated, occasionally criticized by astronomers within the Islamic world, especially, as we will get to shortly. What kept the model standing was not ignorance of its problems. It was the absence, for over a millennium, of anything else that predicted planetary positions as reliably. There's a useful, uncomfortable lesson buried in that fact for anyone paying close attention, one that this documentary will keep circling back to. A theory does not need to be true to be useful for a very long time. It only needs to keep producing correct enough answers that nobody has sufficient reason or sufficient courage to tear the whole structure down and start over. It is also worth remembering that Aristotle's cosmology, which underpinned Ptolemy's geometry, was never purely about astronomy in isolation. It was a complete physical worldview, explaining why heavy objects fall, why fire rises, why the heavens seem permanent while the earth below constantly decayed and changed. Overturning the geocentric model eventually meant overturning an entire interconnected philosophy of physics, not simply relocating a few circles on a diagram. Ptolemy's Almagest was not his only major work, and it is worth noting the darker legacy of his other famous text, the Tetrabiblos, a foundational work of Western astrology. The same mathematician who built astronomy's most influential geometric model also codified much of the astrological tradition that astronomy would spend centuries afterward trying, not always successfully, to separate itself from. It is also worth remembering just how much accurate observational data underpinned Ptolemy's flawed geometric framework. His star catalog, likely built substantially on the earlier work of Hipparchus, listed over 1,000 stars with coordinates precise enough to remain useful reference material for over 1,000 years, even as the theoretical model wrapped around that data turned out to be fundamentally, structurally wrong. It is also worth acknowledging a genuinely competing tradition within Greek astronomy that history mostly buried. Aristarchus of Samos, writing roughly 3.5 centuries before Ptolemy, actually proposed a heliocentric model, correctly placing the sun rather than the Earth at the center, and even attempted to calculate the relative sizes and distances of the sun and moon using geometric reasoning. His idea found almost no lasting support among his contemporaries, dismissed largely because it seemed to contradict both common sense and the absence of any observable stellar parallax. That absence of observable stellar parallax was not, in fact, evidence against a moving Earth. It was evidence that the stars were simply far more distant than ancient astronomers could have reasonably imagined, so distant that any parallax shift was too small to detect with the naked eye. It would take telescopes, and not until the 1830s, for astronomers to finally measure stellar parallax directly and settle a question that had technically been asked and dismissed nearly 2,000 years earlier. It is also worth remembering how the Ptolemaic model's apparent success actively discouraged the kind of careful re-examination that might have exposed its flaws sooner. When a system predicts eclipses and planetary positions well enough for practical use, generation after generation, there is little institutional incentive to question its underlying assumptions. Astronomers spent their careers refining parameters within the existing framework rather than questioning the framework itself, a pattern of incremental patching over structural rebuilding that would recur in different forms throughout much of the history covered in this documentary. It is worth adding one final thought before this chapter closes, tying its central tension directly to the documentary's larger argument. Ptolemy's system did not fail because its author lacked intelligence or rigor. By any reasonable historical standard, the Almagest represents an extraordinary mathematical achievement, and its author was, without question, one of the most capable scientific minds of the ancient world. It failed ultimately because being extremely good at explaining the data you have is not the same thing as being correct about the underlying reality generating that data. It is worth adding a closing thought before we move forward into the centuries that followed. The specific failure mode this chapter describes, mistaking a model that works for a model that is true, would return again and again throughout this documentary, sometimes in astronomy itself, and sometimes in the surrounding culture's confidence about what astronomy had already settled for good. Keep that failure mode in mind. It will resurface sooner than you might expect. Hold onto this exact tension as we move forward, because it will not stay confined to ancient Alexandria. A model that works well enough, defended by enough institutional authority, is remarkably difficult to dislodge, even when quieter, more careful minds elsewhere have already begun finding its cracks. 1,400 years is worth one more moment of honest reflection before we move on. Entire languages rose and fell inside that span. Empires that once seemed permanent collapsed and were forgotten. And still, night after night, students somewhere in the world were being taught the exact same flawed diagram of nested circles and epicycles, trusting it, teaching it forward in turn, mostly without complaint. While much of Western Europe, after the collapse of Rome, drifted away from serious astronomical inquiry, another civilization was doing something close to the opposite. In the 8th and 9th centuries, the House of Wisdom in Baghdad became a center of translation and original research, gathering Greek, Persian, and Indian texts and pushing well past them. The astronomer al-Battani, working near the Euphrates in the 9th century, recalculated the length of the solar year with an error of only a few minutes. He refined Ptolemy's figures on the precession of the equinoxes and the tilt of the Earth's axis, using instruments built with a precision that would not be matched in Europe for centuries. Look at a modern star chart, and you'll find the fingerprints everywhere. Names like Aldebaran, Altair, Betelgeuse, Rigel. Not decoration, direct inheritance from Arabic astronomers like Al-Sufi, whose 10th century book of fixed stars cataloged and named celestial objects with a rigor that European astronomy simply did not possess at the time. These were not isolated geniuses working alone. They were institutions. The observatory at Moraga, built in the 13th century in what is now Iran, employed dozens of astronomers simultaneously, with a library reportedly holding tens of thousands of manuscripts. Later, the observatory at Samarkand, built by the ruler and mathematician Ulugh Beg, produced star catalogs so precise they were still being used as reference material centuries later. Some of this work went further than preservation. Astronomers at Moraga, working within what is now called the Moraga School, identified real mathematical problems with Ptolemy's model, specifically the equant point, a geometric cheat Ptolemy had used to make his circles behave. They built alternative geometric devices to fix it, work that some historians argue Copernicus later drew on, directly or indirectly, centuries afterward. Think about what this chapter is actually asking you to hold in your head. For roughly 600 years, while a common Western narrative imagines a dark, static interval between Rome and the Renaissance, astronomy did not stop. It moved. It just moved somewhere else, carried by scholars whose names most people watching this have never heard. This is a rescue mission that almost no one thinks of as a rescue mission. Without it, the mathematical tools, the corrected star positions, the translated Greek text with centuries of Arabic commentary added, Europe's later reawakening would have had almost nothing solid to reawaken with. Consider the instruments themselves, because the sophistication is easy to undersell from a modern vantage point. The observatory at Samarkand, built in the 1420s under Ulugh Beg, contained a giant Fakri sextant with a radius reportedly around 40 meters, partly buried in a trench cut into a hillside, used to measure the exact angle of celestial objects with a precision that rivaled or exceeded anything produced in Europe for the following century and a half. Ulugh Beg himself was not simply a patron funding other people's work. He was a working astronomer and mathematician, ruler of a Timurid empire stretching across Central Asia, who personally directed the star catalog project bearing his name, listing over 1,000 stars with corrected positions. He was eventually assassinated by his own son in 1449, a brutal reminder that even astronomy's institutional golden ages were built inside violently unstable political worlds. None of this knowledge crossed into Europe instantly or cleanly. It moved through trade routes, through captured texts, through scholars fleeing conflict, through the slow, unglamorous work of translation happening simultaneously in Toledo, Sicily, and elsewhere. By the time a European scholar read a corrected star position originally measured in Moraga or Samarkand, it might have passed through 2 or 3 languages in a century or more of delay. One frequently overlooked figure from this era is Nasir al-Din al-Tusi, working in Moraga in the 13th century, who developed a geometric device now called the Tusi couple, a way of generating straight-line motion out of 2 combined circular motions. Centuries later, this exact mathematical device appears, seemingly reused, in Copernicus's own work, a detail that has fueled genuine scholarly debate over how directly Copernicus may have drawn on earlier Islamic astronomy. The observatory at Moraga, founded in 1259 under the Mongol ruler Hulagu Khan, is a particularly striking example of how astronomy could flourish even in the immediate aftermath of devastating conquest. Hulagu, grandson of Genghis Khan, had just overseen the destruction of Baghdad, yet chose to fund one of the era's most significant scientific institutions, staffed by scholars including the astronomer al-Tusi, who reportedly convinced Hulagu that astrology, and therefore astronomy, could serve the empire's political interests. Al-Battani's refinements went beyond simply improving Ptolemy's numbers. He introduced trigonometric methods into astronomical calculation more systematically than his Greek predecessors had, using sine functions in place of the more cumbersome geometric chord methods the Greeks relied on, a shift that made complex astronomical calculations significantly more tractable and that would directly influence European mathematics centuries later. The observatory at Baghdad, established under the Caliph al-Ma'mun in the 9th century, was not an isolated facility, but part of a broader intellectual project explicitly sponsored by the state, alongside the House of Wisdom's translation efforts. Al-Ma'mun reportedly commissioned astronomers to measure the circumference of the Earth directly, sending survey teams into the desert to measure a degree of latitude along a meridian, arriving at a figure for Earth's size remarkably close to modern measurements. Ibn al-Haytham, working in Cairo in the early 11th century, deserves particular attention for work that extended well beyond pure astronomy into the physics of light itself. His systematic experiments on optics, published in his Book of Optics, established principles of empirical testing and controlled observation that historians of science increasingly credit as a genuine precursor to the modern scientific method, centuries before the term itself existed in Europe. It is worth naming, too, how directly this preserved and expanded body of astronomical knowledge eventually shaped European vocabulary itself, well beyond star names alone. Words like algebra, from the Arabic al-jabr, and algorithm, derived from the name of the mathematician al-Khwarizmi, entered European languages directly through this same channel of transmitted scholarship, a linguistic fingerprint of exactly how much of the mathematical machinery underlying later European astronomy had passed first through Arabic hands. It is worth adding a final thought closing out this chapter properly. Historians of science increasingly reject the older, simpler narrative of a single unbroken relay baton passed cleanly from Greece to the Islamic world to Europe. The reality, as this chapter has tried to show, was messier, more collaborative, more contested, and considerably more interesting, involving genuine original discovery at every stage rather than simple preservation and forwarding of someone else's earlier work. It is worth closing this chapter with a final, direct statement of its actual stakes. Without the sustained institutional commitment of astronomers working across Baghdad, Moraga, and Samarkand, corrected star positions, and preserved Greek mathematics might simply never have survived intact long enough to reach the European scholars who would eventually need them. This was not a footnote to European astronomy's later achievements. It was, quite literally, the bridge those achievements were built across. Hold on to the image of these institutions, funded, staffed, and taken seriously across centuries, as we move toward medieval Europe next. The contrast between sustained scientific investment in one part of the world and its near total absence in another is not a minor historical detail. It shaped directly who got to make the next great discovery and when. It is worth remembering exactly what this chapter has actually been arguing quietly underneath its list of names and observatories. Knowledge does not survive on its own. It survives because specific people in specific places decide it is worth the considerable cost of preserving, refining, and passing forward, even when there is no guarantee anyone downstream will ever properly credit the effort. It is worth adding, one last time, that this whole chapter is really about a single, quiet act of custodianship, carried out across generations, by people who understood, correctly, that a fragile inheritance is only ever as strong as the willingness of strangers to keep protecting it. By the 12th century, translated Arabic texts, many of them themselves translations and expansions of older Greek work, began filtering into the new universities of Europe. Toledo, in particular, became a crossing point, where scholars worked to render astronomical and philosophical texts from Arabic into Latin, often through Hebrew intermediaries, in a slow and imperfect relay of knowledge across 3 languages and 3 faiths. The universities that emerged, Paris, Oxford, Bologna, taught astronomy, but carefully and within firm limits. The framework was Aristotle's, filtered through centuries of church-approved commentary. The Earth sat motionless at the center. Above it, concentric heavenly spheres, incorruptible and perfect, entirely unlike the messy, decaying world below. This was not simply superstition getting in the way of science. It was a coherent, internally consistent worldview, backed by real philosophical argument and reinforced by real institutional power. Questioning it was not just intellectually difficult. It carried genuine social and religious risk. And yet the tools for questioning it were quietly accumulating. Better translations of Ptolemy, corrected star tables from Islamic astronomers, improving instruments, the astrolabe chief among them, letting students measure star positions with a precision earlier medieval scholars simply did not have access to. Mathematics, too, was improving. The reintroduction of Greek geometry, combined with Arabic advances in trigonometry, gave European scholars sharper tools than they had possessed since antiquity. None of this, on its own, broke the geocentric model, but it built the exact kind of technical fluency someone would eventually need to break it. This period rarely gets its own spotlight in popular retellings. It has no dramatic trial, no single defiant genius. It is centuries of quiet, cautious groundwork, students copying diagrams, professors lecturing within careful bounds, mathematics slowly sharpening in the background like a blade nobody has decided to use yet. It would not stay in use for long. In the early 16th century, in a quiet cathedral town in northern Poland, a canon and mathematician named Nicholas Copernicus began working on an idea so dangerous to the established order that he would keep it circulating only among a small circle of trusted friends for over 30 years. It is worth pausing on how genuinely radical the university itself was as an institution, separate from anything it actually taught. The idea of a permanent, self-governing community of scholars, debating, lecturing, examining students on formal logic and natural philosophy, was still new in the 12th and 13th centuries. Astronomy rode into European intellectual life on the back of that new institutional structure, not the other way around. The astrolabe deserves more attention than a single mention. It was functionally an analog computer built centuries before anyone had a word for that concept. A flat brass disc with rotating overlays that let a trained user calculate the time, the positions of major stars, the direction of prayer for Muslim users, or a planet's rough position, all from a single portable instrument small enough to hold in one hand. European craftsmen learned to build increasingly refined astrolabes throughout this period, copying and eventually improving on designs that had themselves traveled from Baghdad through Muslim Spain. Chaucer, better known today for the Canterbury Tales, wrote one of the first technical manuals on the astrolabe in English in 1391, intended for his own young son. Astronomy, by this point, had become ordinary enough to teach a child. It is worth remembering that this era also produced genuine, if cautious, dissent. The 14th century French philosopher Nicole Oersma seriously considered the possibility that the Earth rotated on its axis, working through the physical objections carefully before ultimately declining to endorse the idea outright, citing scripture. The argument existed quietly generations before Copernicus, waiting for someone willing to take the final, dangerous step. Roger Bacon, an English Franciscan friar writing in the 13th century, argued forcefully for the value of direct empirical observation and mathematical proof over blind reliance on ancient authority, a stance that eventually drew suspicion from his own religious order. He was reportedly restricted from teaching for a period, a reminder that the tension between inherited authority and direct observation was already simmering, quietly, well before Copernicus ever put pen to paper. The printing press, introduced to Europe by Johannes Gutenberg around 1440, deserves direct credit as one of the underappreciated forces behind astronomy's eventual reawakening. Before movable type, a single astronomical text might exist in only a handful of hand-copied manuscripts, scattered across a continent, often riddled with copying errors. Printing allowed accurate star tables and translated text to spread quickly and consistently, giving scholars across different cities access to the exact same reliable data for the first time. It is worth naming the specific technical achievement of the equatorium, a mechanical astronomical calculating device developed and refined across Islamic astronomy before reaching medieval Europe. Unlike the astrolabe, designed primarily for observation and timekeeping, the equatorium allowed a user to physically model planetary positions using rotating disks calibrated to Ptolemaic parameters, effectively a hands-on analog simulation of the entire geocentric universe, compact enough to sit on a scholar's desk. Geoffrey Chaucer's own astrolabe treatise, mentioned briefly earlier, is worth returning to for what it reveals about how ordinary astronomical literacy had become by the late 14th century among Europe's educated classes. Chaucer wrote not for fellow scholars, but for a child, walking step by step through basic celestial calculations in plain English prose, evidence that astronomy had migrated, at least partially, out of the exclusive domain of university-trained specialists and into the broader current of everyday literate culture. It is worth closing this chapter by naming exactly what remained conspicuously absent from European astronomy throughout this entire cautious reawakening period, since the absence itself is telling. No European scholar during these centuries seriously proposed moving the Earth from the center of the universe in any surviving, widely circulated text. The mathematical tools were sharpening. The translated knowledge was accumulating. The philosophical courage to actually challenge geocentrism directly had not yet arrived, and it would take one more generation working quietly in Poland before that particular threshold finally got crossed. It is worth adding one final observation about the specific intellectual mood inside these early universities, since it explains why change, when it finally came, felt so sudden to people living through it. Students were trained rigorously in formal logical argumentation, in defending and attacking positions through structured debate, a skill set that, once turned toward genuinely new evidence rather than settled doctrine, proved remarkably well suited to dismantling old assumptions quickly and thoroughly once someone finally worked up the nerve to point that training in a dangerous new direction. It is worth closing this chapter with a final observation about timing. Everything covered here, translated texts, sharpening mathematics, improving instruments, cautious university debate, accumulated across roughly 4 centuries without a single decisive break from geocentric orthodoxy. Then, within the span of little more than a single century, Copernicus, Kepler, and Galileo would each take turns breaking that orthodoxy apart, piece by piece, in rapid, overlapping succession. Slow accumulation, followed by sudden, compressed transformation. That rhythm, too, will recur. Hold on to this quiet, cautious moment as we move forward, because everything about to happen next will feel considerably less cautious. The groundwork laid across these centuries was slow and largely anonymous. What follows will have names, dates, and consequences attached to nearly every single step. Nothing about this reawakening felt, from the inside, like the beginning of a revolution. It felt cautious, incremental, hedged at every step by careful deference to established authority. Revolutions, this documentary keeps finding, rarely announce themselves clearly in advance. They tend to look right up until the very last moment, exactly like careful, patient, unremarkable continuity. It is worth adding, finally, that this whole chapter is a portrait of preparation without confrontation, the exact conditions under which a genuine breakthrough eventually becomes possible, even though nobody living through those centuries could have known that breakthrough was actually coming. Nicholas Copernicus finished the core argument of his life's work decades before anyone outside his closest circle ever read it. A manuscript, quietly circulated among a handful of trusted scholars starting around 1514, proposing something that, stated plainly, sounds almost mundane today. The sun, not the earth, sits at the center. Everything else moves around it. It was not mundane in 1514. It contradicted Aristotle, it contradicted Ptolemy, and depending on how literally you read certain scripture, it contradicted the church. Copernicus was a canon, an official within that same church, with a stable position and a great deal to lose. So he sat on it for nearly 30 years. His final book, On the Revolutions of the Heavenly Spheres, was not published until 1543, the same year Copernicus died. There is a persistent, likely apocryphal story that a printed copy was placed in his hands as he lay on his deathbed, barely conscious, finally holding the argument he had spent his career too afraid to release. Even then, the book shipped with a defensive move built into it. An unsigned preface, added without Copernicus's knowledge by a Lutheran theologian named Andreas Osiander, framed the entire heliocentric model as a useful mathematical fiction. Not a claim about how the universe actually is, just a convenient tool for calculation. That framing likely saved the book from immediate, severe condemnation. It also meant the most dangerous idea in it arrived wearing a disguise, treated by many readers for decades as an interesting calculating device rather than a genuine claim about physical reality. Copernicus himself never saw his idea vindicated. He never saw it seriously debated in public, never saw it tested against real observational proof. He died having handed the world a quiet, hedged, almost apologetic suggestion, and left it entirely unclear whether anyone would ever be brave or reckless enough to insist it was literally true. Someone would be. Not immediately, and not in Poland. The next chapter in this argument belongs to a Danish nobleman with a metal nose, an island observatory, and a level of obsessive precision that had nothing to do with theory and everything to do with simply refusing to stop measuring. Copernicus was not, in the end, working from any new observational data of his own that dramatically outperformed Ptolemy's. His actual telescope did not yet exist, would not for another 60 years. His revolution was almost entirely conceptual, a rearrangement of the same basic set of planetary positions everyone already had access to, viewed through a completely different geometric assumption about what sat at the center. That distinction matters more than it first appears to. Copernicus's model, honestly assessed, was not dramatically more accurate than Ptolemy's at predicting planetary positions. It still used circles, still required extra corrective devices to match observation cleanly, since Copernicus had not yet made Kepler's later leap to ellipses. Its real power was conceptual simplicity, not predictive superiority, and that is a much harder thing to sell to a skeptical institution. It took decades for astronomers to even begin treating heliocentrism as a serious physical claim rather than a clever calculating trick. George Joachim Rheticus, a young mathematician who traveled to study directly under Copernicus and eventually convinced the reluctant, aging canon to finally publish, deserves more credit than history usually grants him. Without Rheticus's persistence, there is a real chance the manuscript never leaves Copernicus's desk drawer at all. The fear Copernicus carried was not entirely paranoid or overstated for its time. Roughly 6 decades after his death, in 1600, the philosopher Giordano Bruno was burned at the stake in Rome, partly over theological heresies, but also for openly promoting an infinite universe filled with countless other inhabited worlds, an idea that extended Copernican thinking into territory the Church found genuinely intolerable. It took roughly a century after Copernicus's death for heliocentrism to gain a genuine, committed following among working astronomers, rather than being treated as a mathematical curiosity. Thomas Digges, an English astronomer writing in 1576, was among the first to publish an explicitly Copernican defense in English, and went further than Copernicus himself had dared, suggesting the stars were scattered through infinite space rather than fixed on a single distant sphere. The mathematical convenience defense that shielded Copernicus's book for decades eventually became impossible to sustain, precisely because later astronomers, Galileo chief among them, insisted on treating the model as literally, physically true rather than a useful abstraction. That insistence is what finally forced the confrontation Copernicus had spent his entire life quietly trying to avoid. It is worth adding a technical detail about exactly what Copernicus's model actually simplified, because the appeal was real even if the model itself remained imperfect. Under Ptolemy's system, explaining the retrograde motion of outer planets required a separate, specifically tuned epicycle for each individual planet. Under Copernicus's heliocentric arrangement, retrograde motion emerged naturally, almost automatically, as a simple consequence of Earth periodically overtaking a slower outer planet in its own orbit, the same way a faster car passing a slower one on a parallel highway makes the slower car briefly appear to move backward against a distant background. That single, elegant simplification, even without perfect predictive accuracy, is arguably what made the Copernican idea so quietly dangerous to defenders of the old system. It did not just offer an alternative answer. It suggested that the entire tangled architecture of Ptolemaic epicycles might be an artifact of asking the wrong question from the wrong vantage point all along, a possibility far more threatening to entrenched authority than a simple factual correction would have been. It is worth adding a final observation about the specific historical timing of Copernicus's caution, since context changes how reasonable his fear actually looks. He was writing in the years immediately surrounding the Protestant Reformation, a period of profound religious upheaval across Europe, when questioning established authority of any kind theological or otherwise, carried genuinely elevated stakes. His decision to delay publication for decades was not simple timidity. It was a calculated survival strategy inside one of the most volatile intellectual climates Europe had experienced in centuries. It is worth adding a final thought closing this chapter, since it sets up the emotional register of everything still ahead. Copernicus died without controversy, without a trial, without any direct personal confrontation over his ideas, largely because he successfully avoided ever forcing the issue during his own lifetime. The confrontation he spent decades quietly dodging did not disappear. It simply waited patiently for someone with less caution and considerably more stubbornness to pick up where he had deliberately left off. It is worth closing this chapter with a final thought about legacy. Copernicus never sought fame, never courted controversy, and by most surviving accounts, genuinely hoped his idea might simply be absorbed quietly into existing astronomical practice without provoking any dramatic confrontation at all. History had other plans for the idea he left behind, and the confrontation he spent his life avoiding would define nearly every chapter of astronomy that followed him for the next century. Hold on to this image of a quiet, careful, frightened man, hedging his own discovery right up until his final breath as we move forward into the next chapter. What comes next will belong to a man with almost none of that caution left in him at all. It is worth sitting one final time with the strangeness of how quietly this particular revolution actually began. No public announcement, no bold declaration, simply a manuscript passed carefully among trusted friends for 3 decades, and a dying man finally, reluctantly, letting it go out into a world he would not live long enough to see argue about it. In 1566, at the age of 19, a Danish student named Tycho Brahe got into a dispute with a fellow nobleman, reportedly over who was the better mathematician. They settled it with swords in the dark, and Tycho lost part of his nose. For the rest of his life, he wore a prosthetic, reportedly made of brass, sometimes described as silver and gold for formal occasions. That detail tends to get told as a quirky footnote. It is worth remembering it as a warning label. The man about to produce the most accurate astronomical data in human history to that point was volatile, proud, occasionally violent, and kept what some accounts describe as a pet elk that reportedly died after drinking too much beer at a party. He was, by any measure, a strange person to trust with the future of astronomy. And yet on the island of Hven, granted to him by the Danish king, Tycho built an observatory called Uraniborg and, working entirely without a telescope, which had not yet been invented, produced star and planetary position measurements accurate to within roughly 1 arc-minute. That is a level of naked-eye precision that stunned astronomers for generations afterward. Tycho did not believe Copernicus. He proposed his own hybrid model, planets orbiting the sun orbiting a stationary Earth, a compromise that satisfied almost no one and turned out to be wrong. But the data he compiled, decades of nightly measurement, would end up matching far more than his theory ever did. In 1600, a young, brilliant, and considerably more socially awkward mathematician named Johannes Kepler joined Tycho as an assistant, largely to gain access to that data. Tycho, by most accounts, guarded his measurements jealously and doled them out to Kepler in frustrating pieces, wary that his assistant might use them to prove Tycho's own model wrong. Tycho died the following year, in 1601, after collapsing at a banquet. Popular legend for centuries blamed a burst bladder from refusing to leave the table for etiquette's sake. Modern forensic analysis of his remains suggests mercury poisoning is at least as plausible, though the exact cause is still debated. Either way, Kepler inherited the full archive of data almost immediately. What Kepler found in that data broke something that had gone unquestioned for nearly 2,000 years. Every astronomer since antiquity had assumed the planets moved in perfect circles, because circles were considered the only shape worthy of the heavens. Kepler tried circles first too. They did not fit Tycho's numbers. Mars, especially, refused to cooperate. So Kepler tried something almost nobody had seriously considered: an ellipse. It fit perfectly, repeatedly, across every planet he tested it against. In 1609, he published the result. The planets do not move in circles. They move in ellipses, with the sun sitting not at the center, but at one of two off-center points called foci. It is worth pausing on how strange this discovery actually is, once you strip away the textbook confidence. A man with famously poor eyesight, using someone else's decades-old measurements, broke a 2,000-year-old assumption about the shape of the universe, not through elegant theory, but through the sheer stubbornness of refusing to force the numbers to lie. Tycho Brahe's observatory complex at Uraniborg was, by the standards of its era, almost absurdly well-funded, essentially its own small research town, complete with a printing press, an alchemical laboratory, a paper mill, and a private prison for tenants who displeased him. He reportedly consumed roughly 1% of the entire Danish crown's budget at the height of his operation, an astonishing commitment of national resources to one man's obsession with the sky. That funding eventually evaporated. After his patron, King Frederick II, died, Tycho fell out of favor with the new Danish court and left the country in 1597, eventually settling in Prague under the patronage of Holy Roman Emperor Rudolf II. It was there, in his final years, that he brought on Kepler, a partnership built on mutual need rather than warmth, each man privately convinced he needed the other more than he wanted to admit. Kepler's path to that partnership was itself unusual. Trained originally as a theology student, deeply religious throughout his life, he came to astronomy partly through a mystical conviction that the spacing of the planets reflected a divine geometric harmony, expressed in his early work through nested Platonic solids, a theory that turned out to be completely wrong, but that reveals how tangled the motives behind real scientific breakthroughs often are. It is genuinely strange and worth sitting with that the man who finally broke astronomy free of 2,000 years of assumed circular motion was chasing what turned out to be a mystical, ultimately false idea about cosmic harmony when he started. The ellipse was not the destination he set out for. It was what he found reluctantly. Honestly, once the numbers refused to agree with the beautiful theory he actually wanted to be true. Kepler's personal life carried its own dark undertone that rarely makes it into the standard telling. His mother, Katerina, was formally accused of witchcraft in 1615, a charge that dragged on for years, and that Kepler, already a respected court mathematician, had to personally help defend against, eventually succeeding in getting her released, though only after she had spent over a year imprisoned and threatened with torture. Tycho's observational technique deserves a closer look because the precision he achieved without a telescope remains genuinely difficult to explain to a modern audience used to digital instruments. He used massive, carefully calibrated sighting instruments, quadrants, and armillary spheres built at enormous scale, specifically to reduce the margin of error inherent in reading an angle by eye, some large enough that multiple assistants were needed to operate a single device. Kepler's third and final major law, published a full decade after the first two in 1619, revealed a mathematical relationship between a planet's orbital period and its distance from the Sun, specifically that the square of the orbital period is proportional to the cube of its average distance. It is a strange, almost hidden pattern, one that would not have been obvious from raw observation alone, and one that later gave Newton crucial evidence for his own theory of universal gravitation decades afterward. It is worth adding context on exactly how good Tycho's naked eye measurements actually were, set against the physical limits of human vision itself. The unaided human eye can typically resolve details down to roughly 1 arcminute of angular separation, and Tycho's instruments, through careful engineering and calibration, pushed observational accuracy close to that theoretical biological ceiling. He was not simply skilled. He was operating astronomy at almost the exact edge of what naked eye observation could ever physically achieve, a ceiling the telescope would shatter within a single generation. Kepler's second law, often overshadowed by the more visually striking first law about ellipses, carries its own quiet elegance. It states that a line drawn from a planet to the sun sweeps out equal areas in equal times, meaning planets move faster when closer to the sun and slower when farther away. It is a law about changing speed, disguised as a law about geometry, and it would later provide Newton with crucial evidence that gravitational force must weaken predictably with distance. It is worth adding a closing thought on exactly how much Kepler's work owed to a kind of scientific integrity that is easy to overlook amid the drama of his personal life. He had a strong personal preference for circular orbits, inherited from centuries of astronomical tradition and his own mystical convictions about cosmic harmony. When 8 arc-minutes of discrepancy between his circular model and Tycho's precise data refused to resolve, Kepler chose to trust the data over his own aesthetic preference, a decision he later described as the wedge that broke astronomy open, a small gap in the numbers that an earlier, less rigorous astronomer might simply have ignored. It is worth adding one final thought on precisely what made this partnership between Tycho and Kepler so productive despite its obvious friction. Tycho supplied decades of unmatched observational precision without the theoretical flexibility to properly interpret it. Kepler supplied exactly that theoretical flexibility, along with a willingness to abandon cherished assumptions, but lacked comparable observational data of his own. Neither man's contribution alone would have broken astronomy free of circular orbits. It took the uncomfortable, occasionally hostile combination of both. It is worth closing this chapter with a final thought about what this partnership ultimately reveals about how real scientific progress actually happens, as opposed to how it gets simplified in retrospect. It rarely arrives through a single isolated genius working in clean, uninterrupted solitude. It arrives more often through friction, through uneven partnerships between people who do not particularly like each other, through decades of unglamorous data collection eventually handed, sometimes reluctantly, to someone else entirely who finally knows what to do with it. Hold on to this image: a broken nose, a jealous data hoard, and an ellipse discovered almost against its finder's own wishes as we move forward. What Kepler had was a shape. What still remained entirely missing for another 70 years was any explanation for why that particular shape was the correct one. It is worth closing on this thought. Astronomy's great leap forward here did not arrive through elegant, effortless genius. It arrived through decades of stubborn, uncomfortable, occasionally petty human effort, a broken nose, a jealous data hoard, a mystical theory that turned out wrong, and a willingness, finally, to trust the numbers over the beautiful idea everyone involved actually wanted to be true. In 1609, roughly the same year Kepler published his laws, an Italian mathematician named Galileo Galilei heard about a new Dutch invention, a device that made distant objects appear closer. He did not invent the telescope. He improved it, built his own, and did something almost nobody else had thought to do with it yet. He pointed it at the sky. What he saw, over the following months, dismantled centuries of assumed certainty one observation at a time. The moon was not a smooth, perfect, incorruptible sphere as Aristotelian cosmology insisted. It had mountains, craters, shadows that behaved exactly like shadows on rough, uneven ground here on Earth. Then, in January of 1610, he found 4 small points of light orbiting Jupiter, moving night to night in a pattern that made no sense unless they were actual moons circling another planet. If objects could orbit something other than the Earth, the entire foundation of geocentric cosmology, everything must revolve around us, was no longer just theoretically questionable. It was visibly, observably false. He kept going. Venus, observed over months, showed a full cycle of phases, crescent to full and back, exactly as it should if Venus orbited the Sun and not the Earth. The Sun itself, viewed carefully, had spots, dark blemishes that moved and changed, further proof against the old idea of a perfect, unchanging heaven. None of this was subtle. Galileo published his findings, defended them publicly, and by the 1610s was arguing openly that Copernicus had been right all along, the sun at the center, the Earth simply one moving planet among several. For a while, he had allies within the church itself, including some Jesuit astronomers who confirmed his telescopic observations. That tolerance did not last. In 1616, the Catholic Church formally declared heliocentrism to be false and contrary to Scripture. Galileo was warned, privately and directly, not to teach or defend the idea as physical truth. For over a decade, he mostly complied, at least on paper. Then, in 1632, he published dialogue concerning the two chief world systems, structured as a debate between three characters. One of them, a defender of the old geocentric view, named Simplicio, was widely read as a thinly veiled mockery of the sitting Pope, Urban VIII, who had once been sympathetic to Galileo. The Pope did not take it well. In 1633, at the age of 69, Galileo was summoned before the Roman Inquisition, threatened with torture, and forced to publicly recant, kneeling, and declare that he did not believe the Earth moved around the sun. Legend holds that he muttered under his breath afterward, and yet it moves. There is no solid historical evidence he actually said it. Whether he did or not, the sentiment was almost certainly true. He spent the remaining 9 years of his life under house arrest, forbidden from publishing further work on the subject, watched, restricted, and slowly going blind. He died in 1642. It would take the Catholic Church until 1992, 350 years later, to formally acknowledge that he had been correct. Sit with that gap for a moment. 3.5 centuries between a man being punished for describing what he could see with his own eyes, through an instrument he built himself, and an institution admitting he had been right. That is the actual cost of being early, not obscurity. Correction, delivered decades too late to matter to the person who earned it. Galileo's conflict with the Church was never purely about astronomy in isolation. It arrived tangled up with questions of scriptural interpretation, ecclesiastical authority, and Galileo's own combative, sometimes tactless personality. He was, by most accounts, a brilliant debater who enjoyed humiliating intellectual opponents in print, a habit that made him formidable allies and formidable enemies in roughly equal measure. It is also worth noting that Galileo was not simply a lone rebel against a uniformly hostile church. Several Jesuit astronomers at the Collegio Romano confirmed his telescopic observations independently within a year of his first publications, and Cardinal Robert Bellarmine, who oversaw the 1616 warning against Galileo, was reportedly open to heliocentrism as a mathematical model, so long as it was not asserted as literal physical truth without further proof. That distinction between useful calculation and literal physical claim is the exact same trap Copernicus's editor had used decades earlier to soften his book. Galileo simply refused to hide behind it. He insisted publicly and repeatedly that heliocentrism was not just convenient. It was true. That insistence, more than the astronomy itself, is arguably what the Inquisition ultimately punished. Galileo's own daughter, Maria Celeste, a nun living in a convent near Florence, wrote him hundreds of surviving letters during his final years, offering emotional support and practical help, including apparently copying and helping preserve some of his manuscripts. Their relationship offers one of the few genuinely tender threads running through an otherwise brutal chapter of astronomy's history, a small human warmth surviving inside an institutional persecution. Galileo's telescope itself was a remarkably modest instrument by later standards, magnifying objects only around 20 to 30 times, with a narrow field of view and noticeable optical distortion around the edges of the image. That he managed to resolve Jupiter's moons and Venus's phases with such primitive equipment is, on its own, a testament to both careful engineering and enormous patience. Hours spent squinting through imperfect glass at objects most people had simply never thought to look at closely. It is also worth remembering that Galileo was not punished merely for holding a belief. He was punished specifically for teaching and publishing it after being explicitly warned not to. The Inquisition's proceedings were built around that formal violation, a technicality that nonetheless allowed the Church to sidestep directly litigating the astronomical evidence itself, focusing the trial instead on obedience rather than on whether the Earth actually moved. It is worth naming the specific instrument Galileo used to observe sunspots without damaging his eyesight, a detail that reveals his broader scientific caution. Rather than staring directly at the sun through his telescope, an act that would have caused permanent blindness, Galileo projected the sun's image onto a flat surface through the eyepiece, a technique called projection that allowed safe, sustained observation of the moving dark blemishes across the solar disk over many consecutive days. The broader European reaction to Galileo's trial extended well beyond Italy itself. René Descartes, working in the Dutch Republic at the time, reportedly delayed or withheld publication of his own physics treatise upon hearing news of Galileo's condemnation, wary of provoking similar consequences. The chilling effect of a single trial rippled outward across an entire continent's scientific community, shaping what other scholars were willing to publish for years afterward. It is worth adding a final note on the broader ripple effect of Galileo's condemnation across European science as a whole. Historians have long debated why the scientific center of gravity shifted noticeably northward in the decades following his trial, toward Protestant England and the Dutch Republic, away from Catholic Italy, which had been a leading center of astronomical and mathematical work for centuries. Galileo's punishment, whatever its precise causal weight, coincided with exactly that broader geographic shift in where scientific risk-taking felt survivable. It is worth adding a final thought closing this chapter, one that carries directly into everything that follows. Galileo's forced silence did not actually silence the astronomy itself. His observations had already been published, read, and independently verified by other astronomers across Europe before his trial concluded. The Church could punish the man. It is worth closing this chapter with a final direct thought about what actually survived from this entire episode. The Inquisition could force a recantation. It could not force the moons of Jupiter to stop orbiting, could not force Venus to stop showing its phases, could not force the physical universe to rearrange itself around a verdict handed down in a Roman courtroom. Galileo's punishment changed what one man was permitted to say out loud. It changed nothing at all about what was actually true. Hold on to this image, a man forbidden from teaching what his own eyes had shown him, as we move into the next chapter. The explanation Galileo lacked, the deeper reason why planets moved the way his telescope proved they did, was about to arrive from an entirely different kind of mind altogether. It is worth closing on this specific thought because it will echo through the rest of this documentary in different forms. Being correct is not the same thing as being safe. Galileo was both entirely correct and, for the final years of his life, entirely unsafe, and history has had to sit with the discomfort of holding both of those facts as true at once. It is worth adding, finally, that Venus itself, the very phases Galileo used as proof against geocentrism, remain visible to anyone today with even a modest pair of binoculars, a small, quiet way to personally repeat the exact observation that once cost a man his freedom. Isaac Newton was, by most contemporary accounts, a genuinely difficult person. Secretive, prone to bitter feuds, capable of holding a grudge for decades. In the 1660s, largely working alone during an outbreak of plague that closed Cambridge University, he began developing ideas about motion, light, and mathematics that he would not fully publish for another 20 years. The popular story, an apple falling from a tree and striking him on the head, is almost certainly exaggerated, though Newton himself, late in life, told a version of it involving watching an apple fall in his mother's orchard and wondering why it always fell straight down rather than sideways or upward. The exaggeration hides something more interesting than the myth. The real question Newton was asking was far stranger than a falling apple. If gravity pulls the apple down, does the same force reach all the way up to the moon? And if it does, why doesn't the moon simply fall into the earth the way the apple falls to the ground? The answer he eventually worked out reshaped physics permanently. The moon, Newton realized, is falling constantly. It is simply moving sideways fast enough that as it falls toward Earth, the ground curves away beneath it at the same rate. Orbit is not the absence of falling. Orbit is falling that never lands. In 1687, encouraged and financially supported by the astronomer Edmund Halley, Newton published Philosophiae Naturalis Principia Mathematica, usually shortened simply to the Principia. In it, he laid out his 3 laws of motion and, critically, the law of universal gravitation. Every object with mass attracts every other object with mass, with a force that depends only on their masses and the distance between them. The word universal is doing enormous work in that sentence. Newton was not describing a special rule for planets and a separate rule for apples. He was claiming, and then mathematically proving, that the exact same force governs a rock falling in an English orchard and a planet tracing Kepler's ellipses around the sun. Heaven and Earth, for the first time, ran on identical physics. This did something to astronomy that no prior discovery had. It stopped being purely descriptive, purely a record of where things happen to be, and became genuinely predictive in a mechanical sense. Given a planet's mass, position, and velocity, you could now calculate, mathematically, where it would be years, decades, even centuries in advance, without any need to consult ancient records or wait and watch. There was a cost to that clarity, and it is worth naming directly. For centuries, the movement of the heavens had carried an aura of divine mystery, planets as symbols, as omens, as evidence of a hand actively arranging the cosmos night by night. Newton's universe ran like a clock, wound up once and left alone, governed entirely by mathematics that required no ongoing supernatural intervention to keep functioning. Some found that comforting. A universe that obeys fixed, knowable laws is, in its own cold way, a reassuring universe. Others found it faintly horrifying, a sky stripped of its mystery and replaced with equations. Either way, astronomy from this point forward would not just observe the heavens. It would predict them, and increasingly, it would go looking for things no one had ever seen. Newton's feud with Robert Hooke, another prominent scientist of the era, is worth a brief mention because it shaped how credit for gravitational theory eventually got assigned. Hooke had proposed, years before the Principia, that gravity might follow an inverse square law and might govern planetary motion. Newton, who despised Hooke personally, minimized his contribution in later editions of his work and famously removed nearly every reference to Hooke he could after Hooke's death. Newton's famous line, "If I have seen further, it is by standing on the shoulders of giants," often read today as a moment of humility, was written in a letter to Hooke and is now widely interpreted by historians as a barbed insult, a reference to Hooke's physical stature, which was notably slight and stooped. Genius, throughout this entire history, keeps arriving bundled together with pettiness, grudges, and very human vanity. The Principia itself was written almost entirely in dense geometric proofs, deliberately difficult, and Newton reportedly admitted he made it hard on purpose, to avoid, in his words, being baited by little smatterers in mathematics. It was not written to be widely read. It was written to be unassailable, a fortress of logic that even his fiercest critics would struggle to find a way inside. Edmund Halley, who funded and pushed Newton to finally publish the Principia, deserves a closing note of his own. Using Newton's own gravitational mathematics, Halley calculated that a comet observed in 1682 followed the same orbital path as comets recorded in 1531 and 1607, correctly predicting it would return again in 1758. He did not live to see the prediction confirmed. The comet still bears his name. Newton's Principia laid out 3 laws of motion that extended far beyond astronomy alone and remain, to this day, the foundation of classical mechanics taught in every introductory physics course. The first law, describing inertia. The second, relating force, mass, and acceleration. The third, stating that every action produces an equal and opposite reaction. Astronomy, in Newton's hands, became simply one application, admittedly the grandest one, of a single unified physical framework. It is worth noting how long it actually took for Newton's ideas to be fully accepted even in his own country, let alone across the English Channel. French scientists, working within a rival Cartesian framework built on the idea of vortices filling space, resisted Newtonian gravity for decades, and it took the mathematician and writer Voltaire, along with his collaborator Émile du Châtelet, publishing accessible explanations of Newton's work in French in the 1730s to meaningfully shift continental opinion. It is worth adding a note on how Newton's law of universal gravitation was eventually tested with extraordinary direct precision, well beyond planetary motion alone. In 1798, over a century after the Principia's publication, the scientist Henry Cavendish conducted a delicate laboratory experiment using a torsion balance, measuring the incredibly faint gravitational attraction between lead spheres in a controlled setting, and from that measurement calculated the density and effectively the mass of the entire Earth itself. This shift from astronomy as celestial observation to astronomy as applied physics changed the kind of person drawn into the field itself. Where earlier chapters of this documentary followed astronomers who were primarily observers, patient watchers of the sky, the era following Newton increasingly rewarded mathematicians, people comfortable translating physical questions into differential equations long before ever picking up a telescope at all. It is worth adding a closing thought on precisely how completely Newton's framework came to dominate scientific thinking for the following 2 centuries, well beyond astronomy alone. His methods, mathematical laws expressed as precise equations, tested rigorously against observation, became the template essentially every other branch of physical science would eventually try to emulate. When Einstein finally revised Newton's picture of gravity in 1915, it was not a rejection of Newton's method. It was, in its own way, the most thorough possible validation of it, proving Newtonian mechanics correct within its own domain while revealing the deeper structure underneath. It is worth adding one final, quieter observation about Newton himself before this chapter closes. Despite reshaping humanity's entire understanding of the physical universe, Newton spent considerable time and energy in private, unpublished study of alchemy and biblical chronology, pursuits that most later scientists would consider entirely outside the bounds of legitimate inquiry. The man who unified heaven and earth under a single mathematical law also spent countless private hours chasing ideas that history has since quietly set aside, a reminder that genius has never arrived free of contradiction. It is worth closing this chapter with a final thought that frames everything still ahead in this documentary. Newton gave astronomy a complete, working, predictive physics of gravity and motion. What he did not give it, and what nobody yet had, was any explanation for why gravity worked the way it did, why mass bent the paths of other masses at all. That deeper question would sit unresolved for over 2 centuries, waiting for a patent clerk in Switzerland to finally take it seriously. Hold on to this image of a clockwork universe, cold, precise, and fully explained, as we move forward. It would take almost exactly 2 more centuries before anyone seriously suggested that clock might contain rooms nobody had thought to check yet, sitting quietly beyond the edge of everything then considered known. It is worth closing on this final thought before the pace of this documentary genuinely quickens. Newton took roughly 2,000 years of scattered observation, from Babylonian tally marks to Kepler's ellipses, and folded it all into a single, unified mathematical framework. That kind of consolidation does not happen often in any field. When it does, it tends to mark the actual hinge point where everything that follows starts moving noticeably faster. It is worth adding, plainly, that this single equation, force equals the product of two masses divided by the square of the distance between them, remains, to this day, accurate enough to plan a mission to the moon or calculate a satellite orbit, even after Einstein revealed the deeper structure sitting underneath it. Every planet known to ancient astronomers, Mercury, Venus, Mars, Jupiter, Saturn, was visible to the naked eye. Humanity had been looking at the same 6 worlds, counting Earth, since before written history. Nobody in 5,000 years of recorded astronomy had ever needed to consider that there might be more. William Herschel was not, by training, an astronomer at all. He was a musician, a composer working in Bath, England, who took up astronomy as an obsessive hobby, grinding and polishing his own telescope mirrors, some of the finest in Europe at the time, largely by hand, often working through the night with his sister Caroline assisting. On the night of March 13, 1781, Herschel was conducting a systematic survey of the sky, cataloging double stars, when he noticed an object that looked wrong. Not point-like the way a star should appear, but slightly disc-shaped. He assumed, reasonably, that it was a comet and reported it as such. It took months of further observation by Herschel and others across Europe, tracking the object's orbit, before the conclusion became unavoidable. Comets have wildly elongated, eccentric orbits. This object's orbit was nearly circular, sitting far beyond Saturn, the outermost planet known since antiquity. It was not a comet. It was a new planet. Herschel initially wanted to name it Georgium Sidus, George's star, after King George III, hoping for royal patronage. The name did not stick internationally. Astronomers eventually settled on Uranus, continuing the tradition of naming planets after figures from classical mythology. The scale of what had just happened is easy to undersell. In a single night, the known boundary of the solar system roughly doubled. For the entire recorded history of human civilization, Saturn had marked the edge of everything. Now, there was something else out there, something no ancient astronomer, no Babylonian scribe, no Ptolemy or Copernicus had ever known to look for. It also cracked open a psychological shift that would keep repeating for the rest of this documentary. The solar system was not a fixed, fully cataloged set of objects handed down by the ancients. It was something you could still discover pieces of if you looked carefully enough and were willing to trust an anomaly instead of dismissing it. Within a few decades, astronomers found more anomalies. In 1801, an Italian astronomer named Giuseppe Piazzi spotted a small object between Mars and Jupiter, initially thought to be a planet and named Ceres, later reclassified as the first known asteroid, once dozens, then hundreds of similar bodies turned up in the same region. The tidy picture of a small handful of planets was starting to come apart at the seams. Caroline Herschel deserves far more than a passing mention as her brother's assistant. Working alongside William for decades, she became a formidable astronomer in her own right, discovering 8 comets and several nebulae, and eventually became the first woman in Britain to be paid a salary for scientific work, granted by King George III in 1787, 6 years after the discovery of Uranus. The sheer physical labor involved in Herschel-era astronomy is easy to forget behind the eventual elegance of the results. William Herschel ground and polished telescope mirrors himself, sometimes working in continuous shifts of many hours, reportedly fed by Caroline directly by hand, so he would not have to stop polishing to eat. This was not a comfortable hobby. It was closer to obsession, carried out at real physical cost. The discovery of the asteroid belt, following Ceres, unfolded gradually rather than all at once. Pallas followed in 1802, Juno in 1804, Vesta in 1807. For a while, astronomers seriously debated whether these small bodies deserved to be called planets at all, a taxonomic argument that would echo, almost exactly, 2 centuries later, when Pluto's own planetary status came under similar debate. Herschel's ambitions eventually extended well beyond a single planet. Using his large telescopes, he cataloged over 2,000 nebulae and star clusters, and correctly theorized that some of these fuzzy patches might be entire separate star systems far beyond our own. A hunch that would not be definitively confirmed for another century and a half, when Hubble finally proved it true with Andromeda. The naming dispute around Uranus dragged on for decades after its discovery, with different European astronomers proposing competing names, including Neptune, oddly enough, and even Herschel, before the mythologically consistent name Uranus, proposed by German astronomer Johann Bode, finally gained broad international acceptance by the early 19th century, roughly 70 years after the planet was first found. It is worth pointing out how strange Uranus itself turned out to be, once later observation revealed more about it. Unlike every other planet in the solar system, Uranus rotates almost entirely on its side, its axis tilted roughly 98 degrees relative to its orbit, likely the result of an ancient, massive collision. The planet that first expanded humanity's sense of the solar system scale turned out to be tumbling through its orbit in a way nothing else nearby does. It is worth situating Herschel's discovery within the broader intellectual mood of the late 18th century, an era already primed by Enlightenment thinking to expect that careful, systematic observation could still overturn inherited assumptions. Herschel's own explicitly stated method, cataloging and re-examining the entire visible sky methodically rather than searching for anything specific, reflects a scientific philosophy that trusted patient completeness over targeted hypothesis, an approach that would pay off again and again throughout the coming centuries of astronomical discovery. The broader public reaction to Uranus's discovery is worth a brief mention, since it reveals how astronomy had begun entering popular culture by the late 1700s in ways it never had before. Newspapers across Europe reported on the new planet with genuine excitement, and Herschel himself was knighted and granted a royal pension, evidence that astronomical discovery had, by this point, become not just a scholarly matter, but a source of genuine national pride and public fascination. It is worth adding a closing observation tying this chapter directly to the one that follows. Herschel's discovery proved something psychologically important that would keep recurring throughout the rest of this documentary. The universe was not simply larger than previously known. It was larger in ways that could still, actively, be found by someone willing to look carefully and systematically at what everyone else had assumed was already fully cataloged. That lesson, learned once with a single planet in 1781, would repeat itself again and again at ever larger scales for the next 2.5 centuries. It is worth adding a final thought closing this chapter. Herschel's discovery did not simply add one new planet to a tidy list. It fundamentally changed what astronomers expected the solar system to be, from a small, closed, fully known set of objects handed down since antiquity into an open-ended frontier that careful, systematic searching could still meaningfully expand. That single shift in expectation, more than the planet itself, is what carried directly into the discoveries still ahead in this documentary. It is worth closing this chapter with a final thought before the documentary's pace begins to noticeably quicken. Everything from this point forward will happen faster, decade by decade, rather than century by century. As instruments improve, institutions multiply, and the sheer number of trained astronomers working simultaneously around the world grows steadily larger. Herschel's solitary, homemade telescope in a bath garden marks something like the last moment in this story where a single dedicated amateur could still meaningfully double the size of the known solar system alone. Hold on to this image, an amateur musician doubling the known solar system by accident as we move forward. The next expansion of scale would not be an accident at all. It would be deliberately calculated, on paper, before a single telescope ever confirmed it was real. It is worth closing this chapter with a brief, direct acknowledgement. The solar system humans had confidently mapped for thousands of years turned out to be smaller than reality by a significant, measurable margin, corrected in a single night by one persistent amateur with a homemade telescope. That correction, small as it might sound stated plainly, quietly reset what every astronomer afterward was willing to assume they already knew for certain. Uranus, once discovered, refused to behave. Astronomers tracking its orbit through the early 19th century kept noticing small, persistent deviations from where Newtonian calculations said it should be. Either Newton's law of gravity was subtly wrong, which seemed almost unthinkable after a century and a half of confirmation, or something else was tugging on Uranus that nobody had accounted for. Two mathematicians, working independently and largely unaware of each other's progress, decided to solve the problem the hard way. Urbain Le Verrier in France and John Couch Adams in England both attempted to calculate the position of an unseen planet using nothing but the mathematics of how its gravity would need to pull on Uranus to produce the observed deviations. This is worth pausing on because it is genuinely strange when you say it plainly. Nobody had seen this planet. Nobody knew for certain it existed. Le Verrier and Adams were trying to locate an invisible object hundreds of millions of miles away, using only the mathematics of how it would need to be tugging on a planet that was itself barely known. In September of 1846, Le Verrier sent his calculated coordinates to the Berlin Observatory. The astronomer Johann Galle pointed his telescope at the specified location that very night. Within about 1 degree of arc of the predicted position, almost exactly where the mathematics said it would be, set a new planet, Neptune. It is difficult to overstate how stunning this confirmation was at the time to anyone who understood what had just happened. Newton's laws had not just described the motion of known objects. They had been used to locate an object that no human being had ever seen, calculated purely from the mathematics of its gravitational influence on something else. While the solar system was being mapped with this new mathematical precision, an entirely different kind of question was opening up around the stars themselves. In 1814, a German optician named Joseph von Fraunhofer, studying sunlight passed through a prism, noticed hundreds of thin, dark lines interrupting the rainbow spectrum, gaps where certain colors were simply missing. It took decades to fully understand what those lines meant. By the 1850s and 1860s, physicists including Gustav Kirchhoff and Robert Bunsen established that each chemical element, when heated, produces or absorbs light at its own specific, unique set of wavelengths, a kind of fingerprint. Those dark lines in sunlight were the fingerprints of elements sitting in the sun's outer atmosphere, absorbing their own specific colors. This meant something enormous and slightly deflating all at once. Stars were not mysterious, unknowable points of divine light. They were chemically analyzable. You could point an instrument at something hundreds of trillions of miles away and determine, with real confidence, what elements it was made of. The universe was becoming more knowable by the decade, and simultaneously, somehow, colder. There's a bitter postscript to the Neptune story that rarely makes it into the shorter tellings. John Couch Adams had actually completed his own calculations, independently, roughly a year before Le Verrier, and had sent them to the Astronomer Royal in England, George Airy. Airy, for reasons that remain debated by historians, did not pursue the search with any urgency, and England lost the priority race to France almost entirely through institutional delay rather than any lack of scientific merit on Adams's part. The resulting dispute over credit grew genuinely bitter, drawing in national pride on both sides of the English Channel, with French and British newspapers each championing their own mathematician. The scientific consensus that eventually settled the argument gave both men substantial credit, a rare diplomatic outcome to what could easily have remained an ugly, decades-long grudge between two national scientific establishments. The spectroscopic revolution, meanwhile, kept expanding well beyond simply identifying known elements in starlight. In 1868, Astronomers Norman Lockyer and Pierre Janssen independently detected a spectral line during a solar eclipse that matched no known element on Earth. Lockyer proposed a new element entirely, naming it helium, after Helios, the Greek god of the sun. It would not be isolated on Earth itself for another 27 years. The spectroscopic method that revealed helium in the sun would go on to become one of astronomy's single most powerful tools, eventually letting scientists determine a star's temperature, composition, motion, and age, all from analyzing light that traveled for potentially millions of years before ever reaching a telescope on Earth. It remains, to this day, largely the same underlying technique astronomers use to study distant stars and galaxies. It is worth stating clearly what made the Neptune prediction such a uniquely powerful test of Newtonian physics, because the stakes were genuinely high. Had astronomers pointed their telescopes at Leverrier's calculated coordinates and found nothing there, it would have represented one of the most serious challenges to Newton's law of gravity in over a century and a half. The fact that Neptune sat almost exactly where the mathematics said it must be removed, for most working scientists, essentially any remaining doubt about the universal reach of Newtonian gravitation. Spectroscopy's reach kept extending well past identifying elements. By the late 19th century, astronomers realized that the exact pattern of shift in a star's spectral lines could reveal its velocity directly toward or away from Earth, the same Doppler principle later used to detect exoplanets and to measure the redshift of entire distant galaxies. A single physical insight, first applied to sound waves, ended up threading through nearly every major discovery covered in the second half of this documentary. It is worth adding one further detail about the sheer difficulty of the Neptune search itself. Once Leverrier's coordinates were in hand, Johann Galle, at the Berlin Observatory, succeeded quickly in part because he happened to have access to a recently completed, highly detailed star chart of that specific region of sky, allowing him to immediately recognize an object that did not match any previously cataloged star. Without that particular chart, sitting ready on his desk that exact night, the confirmation might easily have taken considerably longer. It is also worth noting that Galileo himself, over 2 centuries earlier, had almost certainly observed Neptune without realizing what he was looking at. His own detailed notebooks from December 1612 and January 1613 record a faint point of light near Jupiter that modern astronomers, retracing his recorded positions, have identified as very likely being Neptune itself, unrecognized at the time simply as a background star. The 8th planet, in other words, had technically already been seen and dismissed once before, roughly 234 years before anyone understood what it was. It is worth adding a final thought connecting the mathematical triumph of Neptune's discovery to the chemical revelations of stellar spectroscopy unfolding at almost exactly the same historical moment. 19th century astronomy was proving, on 2 completely separate fronts simultaneously, that the universe operated according to the exact same rules governing matter and motion here on Earth. The planets obeyed the same gravity as a falling apple. The stars were built from the exact same chemical elements found in an earthly laboratory. The heavens, piece by piece, were losing whatever remained of their ancient claim to being made of some fundamentally different, unknowable substance. It is worth adding a final thought closing this chapter properly. Neptune's discovery represented, in a very real sense, the high watermark of pure Newtonian confidence, a moment when mathematics predicted physical reality with such precision that doubt itself seemed almost unreasonable. The chapters still ahead in this documentary will show that same confident, mechanical universe beginning to develop cracks of its own, cracks that would eventually require an entirely new physical framework to properly explain. It is worth closing this chapter with a final thought tying its 2 separate threads together properly. Both the discovery of Neptune and the birth of stellar spectroscopy shared a common underlying confidence that the universe was governed by consistent, discoverable rules, whether gravitational or chemical, and that patient, Careful mathematics could reveal those rules, even in objects no human being would ever physically touch or visit. That confidence would be tested severely by what came next. Hold on to this image, a planet found through pure mathematics and a star's chemistry cracked open by a prism as we move forward. Both discoveries shared the same quiet confidence that the universe obeyed consistent rules. That confidence was about to face its strangest test yet, over the true size of the universe itself. It is worth closing this chapter with one final observation. Two entirely separate methods, pure orbital mathematics on one hand and the chemistry of light itself on the other, converged in the same few decades to prove the same underlying point from different directions. The universe was consistent. Its rules did not change depending on where or how carefully you happen to look. For most of recorded astronomical history, the Milky Way was simply assumed to be the entire universe. Astronomers had cataloged faint, fuzzy patches of light scattered across the sky, calling them nebulae, and largely assumed they were clouds of gas or forming star clusters, all contained safely within our own galaxy. Some astronomers disagreed, and the disagreement eventually became formal. On April 26, 1920, at the Smithsonian Museum of Natural History in Washington, two astronomers, Harlow Shapley and Heber Curtis, held a public debate later remembered simply as the Great Debate, arguing over the true scale of the universe. Shapley argued the Milky Way was enormous, essentially the entire universe, and that these spiral nebulae were relatively small, nearby objects within it. Curtis argued the opposite, that at least some of these spiral nebulae were entire separate galaxies, island universes in their own right, sitting at vast distances far outside our own. Neither man, at the time, had definitive proof. The proof arrived a few years later, from an astronomer working at the Mount Wilson Observatory in California with access to the largest telescope in the world at the time, the 100-inch Hooker telescope. His name was Edwin Hubble. Hubble's key tool was a specific type of star called a Cepheid variable, a star whose brightness pulses in a regular, predictable cycle, and whose pulse period is directly tied to its true intrinsic brightness. Find a Cepheid, measure how its brightness changes over time, and you can calculate exactly how bright it actually is, then compare that to how dim it appears from Earth to calculate its distance. In 1923 and in 1924, Hubble found Cepheid variable stars inside the Andromeda Nebula. He calculated their distance. The number that came back was not merely large. It was roughly 900,000 light-years, later refined and corrected to a figure closer to 2.5 million light-years, a distance so far beyond the known edge of the Milky Way that the conclusion was unavoidable. Andromeda was not a nebula inside our galaxy. It was an entire separate galaxy, comparable in scale to our own, sitting at a distance that made the previously assumed size of the entire universe look almost provincial by comparison. It is genuinely difficult to convey the disorientation this must have caused even to trained astronomers. Imagine spending your entire career assuming a single house is the whole world, and then discovering, with hard mathematical proof, that the house sits inside a city and the city inside a country, and you have no idea yet how large the country actually is. Within a few years, Hubble had identified dozens more of these island universes, entire galaxies scattered across distances that made even Andromeda look close. The universe, which had already grown from a single ancient Earth to a vast solar system to an enormous Milky Way, had just multiplied again, and there was, as of yet, no reason to believe it would stop. Henrietta Leavitt, working as one of the human computers at Harvard College Observatory in the early 1900s, deserves direct credit for making Hubble's entire discovery possible, a fact that is still underemphasized in most popular retellings. In 1908, and more fully in 1912, Leavitt discovered the precise relationship between a Cepheid variable star's pulse period and its true brightness, the exact tool Hubble would later use to measure Andromeda's distance. Leavitt worked for a fraction of the pay afforded to male astronomers at the time, in a role explicitly limited to data analysis rather than independent research or telescope access. She never received a Nobel Prize, though a Swedish mathematician later attempted to nominate her, only to learn she had already died of cancer in 1921, years before Hubble's confirmation made her discovery famous. It is worth being honest about this pattern, because it recurs throughout astronomy's history, and this documentary has already touched it more than once. The person who builds the essential tool and the person credited publicly with the breakthrough are not always the same person, and the gap between them tends to fall along exactly the lines you would expect, given who held institutional power at the time. The scale of Hubble's own instrument deserves a moment of attention. The 100-inch Hooker telescope, completed in 1917 atop Mount Wilson above Los Angeles, remained the largest operational telescope on Earth for over 3 decades. Hubble had access to genuinely unprecedented light-gathering power, and even then, resolving individual Cepheid stars inside a separate galaxy pushed the instrument close to its absolute limit. It is worth naming exactly how disorienting the shift in scale actually was for working astronomers at the time, because modern audiences, already accustomed to a universe of billions of galaxies, can struggle to feel the shock properly. Before Hubble's 1923 measurement, serious, credentialed astronomers, Harlow Shapley among them, genuinely believed the Milky Way likely constituted the entire physical universe. Hubble's data did not refine that belief. It obliterated it in the space of a single calculation. Hubble himself, notably, was cautious in how he framed the initial result, reportedly reluctant to publicly declare victory in the Great Debate before he felt the data was airtight. He sent his findings first in a private letter to Harlow Shapley, the very astronomer whose position his discovery directly undermined. Shapley reportedly read the letter and remarked to a colleague that it had destroyed his universe, a strikingly personal way to describe a strictly scientific result. It is worth adding a technical clarification about exactly how a Cepheid variable star's pulsation actually works physically, since the mechanism itself is genuinely elegant. These stars pulse because a specific layer of partially ionized helium in their outer atmosphere alternately traps and releases heat, causing the star to physically expand and contract in a regular cycle. And larger, intrinsically brighter Cepheids pulse more slowly than smaller, dimmer ones, producing exactly the predictable relationship Henrietta Leavitt first identified in the data. The broader implication of Hubble's Andromeda measurement extended well beyond simply resizing the universe once. It established, for the first time, a genuinely reliable method for measuring distances to other galaxies at all, a technique astronomers refer to today as a standard candle. That single method, refined and extended across the following century, remains one of the fundamental tools underlying essentially every subsequent measurement of the universe's scale and expansion covered in the chapters still ahead of us. It is worth closing this chapter by naming precisely how quickly astronomical thinking had to reorganize itself around Hubble's result. Textbooks, lectures, and the entire working vocabulary of professional astronomy needed updating within a matter of a few short years, an adjustment that, set against the glacial multi-century pace of earlier paradigm shifts like the Copernican revolution, represented an entirely new, much faster rhythm of scientific change, one that the remaining chapters of this documentary will show accelerating even further. It is worth adding a final thought closing this chapter, one that bridges directly into what comes next. Hubble's proof that the universe contained billions of separate galaxies naturally raised an obvious follow-up question that took several more years to properly answer. If there are billions of galaxies scattered across the universe, are they simply sitting still out there, fixed in place, or are they moving? The answer to that question, discovered by the same astronomer only a few years later, would prove even more disorienting than the first. It is worth closing this chapter with a final thought on scale itself, since scale is the actual subject running underneath this entire documentary. Every chapter so far has involved some kind of expansion in time, in distance, in the sheer number of objects known to exist. Hubble's discovery of Andromeda's true distance represents, arguably, the single largest one-time jump in scale this documentary will cover, and even it, as the next chapter shows, was only a modest preview of what remained to be found. Hold on to this image, an entire second galaxy hiding inside what everyone had assumed was a nearby cloud of gas. As we move forward, the universe had just gotten enormously larger in a single measurement. It was about to get considerably stranger once physicists started asking what the empty space between all those galaxies was actually made of. It is worth closing this chapter with a final, direct thought. Every astronomer working before 1923 had built their entire career inside a universe that was, without anyone realizing it, dramatically smaller than the real one. That is a genuinely humbling thing to sit with. And this documentary is about to ask you to sit with an even larger version of that exact same humility repeatedly for the remainder of its runtime. In 1915, Albert Einstein published his general theory of relativity, and in doing so, quietly detonated Newton's clockwork universe from underneath. Newton had described gravity as a force acting instantly across empty space between two masses. Einstein described something stranger. Space and time are not a fixed, empty stage. They are a single, flexible fabric, and mass bends that fabric. A planet does not orbit the sun because the sun is pulling on it across empty distance. A planet orbits the sun because the sun's mass curves the space around it, and the planet is simply following the straightest possible path through curved geometry. Gravity, in this picture, is not a force at all. It is geometry. This was confirmed dramatically in 1919, when astronomer Arthur Eddington led an expedition to observe a solar eclipse and measured starlight bending around the sun's mass by almost exactly the amount Einstein's equations predicted, a deviation Newtonian physics could not fully account for. The confirmation made international headlines and made Einstein, almost overnight, a global celebrity. But buried inside Einstein's equations was something far stranger than bending starlight, something that emerged almost as an unwanted side effect of the mathematics rather than a deliberate prediction. In late 1915 and into 1916, a German physicist named Karl Schwarzschild, while serving on the front lines of World War I, worked out an exact solution to Einstein's equations for the space surrounding a single, non-rotating mass. Schwarzschild's solution contains something disturbing. If you compressed enough mass into a small enough radius, the equations predicted a boundary, a point where the curvature of space-time became so extreme that nothing, not even light, could travel fast enough to escape it. A region cut off from the rest of the universe, permanently and completely. Almost nobody, including Einstein himself, believed this was physically real. It looked like a mathematical curiosity, a strange edge case in an equation, not something nature would actually go and build. Einstein published a paper in 1939 specifically arguing that such an object could never actually form in reality. He was on this particular point wrong. The term black hole would not even be popularized for decades, generally credited to physicist John Wheeler in the late 1960s. For most of the mid-20th century, this object existed only as an unsettling theoretical possibility, discussed in academic papers, dismissed by many serious physicists as an artifact of imperfect mathematics rather than a genuine feature of the universe. It is worth sitting with that dismissal for a moment, because it says something about how physicists in this era related to their own equations. Sometimes the mathematics tells you something true long before anyone is emotionally prepared to believe it. It would take direct observational confirmation, decades away, before the scientific community stopped treating black holes as a theoretical embarrassment and started treating them as one of the most important objects in the entire universe. Einstein arrived at general relativity only after nearly a decade of grinding, frustrating mathematical labor, following his earlier, far more immediately celebrated theory of special relativity in 1905. He reportedly told a friend that compared to the problem of gravity, special relativity had been child's play. He needed help from mathematician friends, particularly Marcel Grossman, to master the differential geometry required to even express his ideas properly. The 1919 eclipse expedition that confirmed his theory was itself a quietly remarkable act, organized and championed by Arthur Eddington, a British Quaker and pacifist, to test the theory of a German physicist, published in the middle of the First World War at a moment when British and German scientific institutions were largely estranged by the conflict. Science, for a brief moment, crossed a line that politics had drawn as absolute. Karl Schwarzschild, whose equations first hinted at black holes, never lived to see any part of his work's later importance. He developed his solution while serving as an artillery officer on the Russian front, contracted a rare and painful autoimmune skin disease during his deployment, and died in 1916, only a few months after submitting his paper, at the age of 42. Einstein's general relativity also predicted something else astronomers would only confirm decades later: gravitational lensing on a much larger scale than a single eclipse test could show. Massive galaxy clusters bend and magnify the light of even more distant galaxies behind them, sometimes producing multiple distorted images of a single background object, a direct, visible consequence of space-time curvature now routinely used to study the earliest, faintest galaxies in the universe. The concept of a black hole's event horizon, the boundary of no return, is worth explaining a bit more precisely than the earlier chapter had room for. It is not a physical surface, not a wall or membrane in any material sense. It is simply the distance from the black hole's center at which the escape velocity, the speed needed to break free of its gravity, exceeds the speed of light itself, the fastest speed anything in the universe is permitted to travel. General relativity also produced a specific, testable prediction about how light behaves near extremely massive objects, one that goes beyond simple bending. Time itself, the theory predicts, runs measurably slower in stronger gravitational fields, an effect called gravitational time dilation, later confirmed with remarkable precision using atomic clocks placed at different altitudes on Earth, and now factored directly into the operation of GPS satellites, which would drift and become useless within hours if Einstein's corrections were ignored. It is worth adding, for context, exactly how radically general relativity departed from everyday human intuition about gravity in a way that even brilliant contemporaries initially struggled to fully accept. Einstein's equations implied that a sufficiently massive object could not simply attract nearby matter across empty space, as Newton had described, but could actually warp the geometric structure of space and time themselves, a claim so abstract that it took years of careful, independent verification before the broader physics community treated it as settled fact rather than elegant speculation. It is worth noting, too, that Einstein's own resistance to black holes was not simply stubbornness. His 1939 paper attempted a genuine mathematical argument, showing that a rotating cluster of particles could not, under the specific conditions he modeled, collapse past a certain critical radius. The argument was reasonable within its narrow assumptions. It simply did not account for the far more general collapse scenarios that later physicists, including Robert Oppenheimer in 1939 as well, working independently, would show could indeed produce exactly the kind of total collapse Einstein had hoped to rule out. It is worth closing this chapter with a final thought on the peculiar emotional texture of theoretical prediction, something this documentary keeps returning to in different forms. Schwarzschild's mathematics described black holes in 1916. Direct observational proof would not arrive for over half a century. For decades, an entire category of the most extreme objects in the universe existed only as ink on paper, believed by some, dismissed by others, real regardless of which side turned out to be correct, waiting patiently for instruments capable of actually finding one. It is worth adding one final thought closing this chapter. General relativity and the theoretical black hole it predicted represent something genuinely new in this documentary's story. The first time astronomy's boldest claim about the universe arrived entirely from pure mathematics, years or even decades ahead of any possible observational test. Every previous major shift covered so far had observation leading and theory following close behind. Here, for the first time, theory pulled dramatically ahead, and the universe would need decades to catch up and confirm it. It is worth closing this chapter with a final thought that carries directly forward. Black holes remained, at the end of this era, a genuinely open question, believed by some, dismissed by others, entirely unconfirmed by direct evidence. That uncertainty is worth sitting with for a moment before moving on, because it captures something important about how this documentary story actually works. Not every chapter ends with resolution. Some simply end with a question still hanging in the dark, waiting its turn. Hold on to this image, a mathematical monster nobody quite believed in yet, sitting quietly inside Einstein's own equations as we move forward. The universe, it turns out, was about to reveal something even stranger than a hidden collapsed star. It was about to reveal that the whole thing was moving. It is worth closing this chapter with a final, quiet thought. Even Einstein, the single mind most responsible for reshaping how astronomy understood gravity itself, could be wrong about the direct consequences of his own equations. Genius, this documentary keeps demonstrating from every possible angle, has never once meant infallibility. Not for Ptolemy, not for Newton, and not for Einstein either. It is worth adding, finally, that Schwarzschild wrote to Einstein directly from the war front, sending his solution by mail between artillery postings, a detail that makes the whole discovery feel even stranger set against its actual, brutal historical backdrop. Edwin Hubble was not finished after proving Andromeda was a separate galaxy. Working with fellow astronomer Milton Humason at Mount Wilson through the late 1920s, he began measuring something called redshift in the light coming from dozens of distant galaxies, a stretching of light toward longer, redder wavelengths, similar to how a siren's pitch drops as it moves away from you. In 1929, Hubble published a paper containing a pattern that should not have made sense under a static, unchanging universe. Nearly every galaxy he measured showed redshift, meaning nearly every galaxy was moving away from us. And the farther away a galaxy was, the faster it appeared to be receding. Picture that for a moment, honestly, without the textbook detachment. Every direction you look, everything out there is running away from you, and the further it already is, the faster it is fleeing. That is not a comfortable pattern to sit inside. It sounds at first glance like you are standing at the center of some cosmic act of rejection. The actual explanation is stranger and somehow less personal. It is not that galaxies are flying through static space away from us specifically. It is that space itself is stretching, expanding, carrying galaxies apart the way raisins in a rising loaf of bread drift apart from each other. Not because any raisin is moving through the dough, but because the dough itself is expanding everywhere at once. Run that expansion backward, mathematically, and the implication becomes unavoidable. If everything is moving apart now, then in the past, everything must have been closer together. Follow that logic back far enough, and you arrive at a moment when the entire observable universe, everything, all matter, all space, was compressed into an unimaginably small, dense point. This idea did not land smoothly. Some astronomers and physicists found it philosophically uncomfortably close to a religious creation narrative dressed up in mathematics, a universe with a definite beginning rather than one that simply, eternally, always was. The Belgian physicist and Catholic priest Georges Lemaitre had actually proposed a version of this expanding universe model even before Hubble's observations, in 1927, and faced real skepticism, some of it explicitly tied to the theological overtones of a cosmic starting point. One of the most prominent skeptics, astronomer Fred Hoyle, championed a rival idea called the steady-state theory, in which the universe has always existed roughly as it is now, with new matter continuously created to fill the gaps as galaxies drift apart. Hoyle, somewhat famously, coined the term Big Bang in a 1949 radio broadcast, and by most accounts he meant it dismissively, mockingly, as a jab at an idea he considered absurd. The name stuck anyway. For decades after Hubble's discovery, the Big Bang remained a theory, a mathematically consistent implication of an expanding universe, but not something anyone had directly observed. It explained the redshift data well. It made testable predictions. What it did not yet have was a smoking gun, some physical trace left over from that original moment that scientists could actually detect and measure. That smoking gun was out there. It had been traveling unnoticed across the entire universe for billions of years, and it was about to be found almost by accident by two engineers who were not looking for the origin of the universe at all. They were just trying to figure out why their radio antenna would not stop humming. Vesto Slipher, working quietly at the Lowell Observatory in Arizona over a decade before Hubble's famous paper, had already measured redshift in a number of spiral nebulae as early as 1912, finding that most were moving away from us at surprisingly high speeds. Slipher's careful, largely unglamorous spectroscopic work provided the raw velocity data that both Hubble and Lemaitre would later build directly upon. Georges Lemaitre's story deserves a fuller telling than a single mention allows. A Belgian priest who earned a doctorate in physics at MIT, Lemaitre proposed his expanding universe model and its logical implication of what he called a primeval atom in a relatively obscure 1927 journal, published in French, that most of the international astronomical community simply did not see for several critical years. Einstein himself, upon first hearing Lemaitre present the idea in 1927, reportedly told him his physics was correct, but his interpretation was abominable, unwilling at the time to accept the idea of a universe with an actual beginning. Einstein had, at that point, already inserted a fudge factor into his own equations, later called the cosmological constant, specifically to force his math into predicting a static, unchanging universe, an adjustment he later called his own biggest blunder. The rivalry between the Big Bang model and Fred Hoyle's steady-state theory continued, genuinely unresolved among serious physicists, for roughly 2 more decades after Hubble's 1929 finding. It would take until the mid-1960s and a very specific piece of accidental evidence discovered in New Jersey for the argument to finally settle in one direction, decisively and for good. It is worth revisiting exactly what kind of resistance Lemaitre and Hubble's expanding universe idea faced from a purely scientific, rather than religious, standpoint. Many physicists in the 1920s and 1930s were trained within a deeply ingrained assumption, inherited partly from centuries of Newtonian stability, that the universe as a whole must be static, eternal, and unchanging on the largest scales, a philosophical preference that took real observational force to finally overturn. Milton Humason, Hubble's key collaborator at Mount Wilson, is a figure worth pausing on briefly. He began his career at the observatory not as a trained scientist, but as a mule driver, hauling construction materials up the mountain during the telescope's building, and worked his way up through the ranks to become one of the most skilled observers on staff, eventually co-authoring some of the most important redshift measurements in the entire history of cosmology. It is worth adding a further note on precisely how astronomers eventually distinguished between the Big Bang model and the rival steady-state theory, using observational evidence beyond the cosmic microwave background alone. Careful surveys of distant radio sources through the 1950s and early 1960s found that such sources were noticeably more common in the distant, and therefore much younger, universe than the nearby, more recent universe. Direct evidence that the universe's contents had genuinely changed and evolved over cosmic time, a finding flatly incompatible with a truly static, eternally unchanging steady-state model. It is worth stating plainly how personally difficult this shift proved for Fred Hoyle himself, who remained a committed and vocal skeptic of the Big Bang model for the rest of his career, even after the cosmic microwave background discovery had convinced nearly the entire rest of the astronomical community. Scientific consensus, this documentary keeps demonstrating, rarely arrives instantly or unanimously, even when the underlying evidence has, in retrospect, become genuinely overwhelming. It is worth closing this chapter by naming the emotional undercurrent running beneath the purely scientific debate over the universe's origin. A universe with a definite beginning implies, whether physicists were comfortable with it or not, the possibility of a definite ending as well. The same redshift data proving cosmic expansion also opened an unavoidable question about the universe's eventual fate, whether it would expand forever, collapse back on itself, or do something else entirely, a question this documentary will return to only briefly, since the honest answer remains genuinely unresolved even today. It is worth adding a final thought closing this chapter properly, since the discomfort described here did not resolve quickly or cleanly. For nearly 4 decades after Hubble's 1929 redshift measurement, the scientific community remained genuinely split on whether the universe truly began at a single point or had simply always existed in some steady, self-renewing form. That split would not close through further mathematical argument alone. It would take a specific, physical, almost accidental piece of evidence, discovered by 2 men who are not even looking for it, to finally settle things. It is worth closing this chapter with a final thought before the story's climax properly begins. Everything covered across the preceding 14 chapters, from tally marks to Einstein, had been building, whether anyone realized it or not, toward a single unresolved question. Did the universe have a beginning? That question was no longer simply philosophical by 1929. It had become, for the first time in human history, a genuinely testable scientific one, and the test was coming soon. Hold on to this image. Every galaxy in the sky fleeing from every other galaxy as we move forward. The theory said this pointed back toward a single origin point. What the theory still lacked for several more decades was anyone actually finding physical proof of that origin still sitting out there, waiting to be detected. It is worth closing this chapter with a final, direct thought before the story's true climax begins. For nearly 4 decades, the biggest question in all of cosmology sat completely open, argued over at conferences, debated in journals, resolved by neither side through argument alone. Some questions, this documentary keeps proving, simply cannot be settled by cleverness. They have to wait for the universe itself to hand over the evidence. In 1964, at Bell Telephone Laboratories in Homedale, New Jersey, 2 radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna, originally built for satellite communication, that they had repurposed for radio astronomy research. They kept picking up a faint, steady hiss of noise coming from every direction in the sky, at all times, regardless of where they pointed the instrument. Their first assumption was equipment failure. They checked every possible source of interference. They found pigeons nesting inside the antenna and carefully removed them, along with what Penzias later described, somewhat delicately, as an accumulation of what he called white dielectric material. The noise did not go away. They ruled out nearby radio interference. They ruled out the antenna's own electronics. They ruled out New York City, a nuclear test that had occurred years earlier. Everything they could think of. The hiss remained exactly the same. Uniform, constant, coming equally from every direction, day and night, in every season. At almost the exact same time, roughly 30 miles away at Princeton University, a team led by physicist Robert Dicke was actively theorizing about and preparing to search for exactly this kind of signal. If the Big Bang had actually happened, the theory went, the extreme heat of that initial moment should have left behind a faint, cooled remnant of radiation, spread uniformly across the entire sky, now stretched by billions of years of cosmic expansion into the microwave range. A colleague connected the 2 groups. When Dicke's team examined Penzias and Wilson's data, The match was immediate and unmistakable. The uniform, inexplicable hiss coming from Homedale was not equipment malfunction. It was the cosmic microwave background, radiation left over from a time roughly 380,000 years after the Big Bang, when the universe first cooled enough for light to travel freely. Reportedly, upon hanging up the phone with Dick's team, Robert Dick turned to his colleagues in a room and said something to the effect of, "Well, boys, we've been scooped." It is a small, almost gentle detail, a rival team's leader reacting to being beaten to a discovery not with bitterness, but with a kind of resigned respect for what had just been confirmed. There is something worth dwelling on in how this discovery actually happened. It was not found by cosmologists, searching deliberately for the universe's origin, with a carefully designed experiment built for that exact purpose. It was found by two engineers, trying to eliminate what they assumed was an annoying, persistent flaw in their own equipment, and stumbling instead into physical proof of the beginning of everything. Penzias and Wilson received the Nobel Prize in Physics in 1978 for a discovery they had not, at the time, fully understood the significance of. The universe's origin was no longer a theoretical implication drawn from redshift data and extrapolated backward on paper. It was now an observed, measured, physical fact sitting in the noise of a New Jersey radio antenna, waiting the entire time for someone to stop trying to get rid of it. With the beginning confirmed, astronomers turned their attention, with new urgency, toward the most extreme consequences that beginning could still be producing out there right now. The theoretical monsters Einstein had dismissed and Schwarzschild equations had predicted decades earlier were about to stop being a mathematical curiosity and start being an observational target. The scale of the coincidence involved in the discovery deserves its own moment of attention. Two entirely separate teams, working roughly 30 miles apart in New Jersey, one actively theorizing about a signal, the other accidentally detecting it while trying to make an unrelated satellite antenna function properly, arrive at the exact same conclusion within weeks of each other, purely because a mutual colleague happened to connect them by phone. Had that phone call not happened, or happened months later, the history books might read differently. Robert Dick's team at Princeton was actively building their own dedicated antenna to search for the same background radiation, unaware that a fully functional, far more sensitive instrument already existed just down the road, currently being used to complain about pigeon droppings. The cosmic microwave background, once mapped in far greater detail by later satellite missions, including COBE in the 1990s and Planck in the 2010s, turned out to contain something almost as important as its mere existence. Tiny, faint temperature variations, fractions of a degree, scattered across the otherwise uniform glow. Those tiny ripples are now understood as the seed from which every galaxy, star, and planet, including our own, eventually grew. The precision of later cosmic microwave background measurements is genuinely staggering. The Planck satellite, operating in the 2010s, measured the temperature of this leftover radiation to be approximately 2.725 degrees above absolute zero, uniform across the sky to within a precision of about 1 part in 100,000. A number so consistent it functions almost as a fingerprint confirming the universe's early, extremely hot and dense state. It is worth naming what the cosmic microwave background actually looks like when properly visualized, because the raw description undersells its strangeness. Modern satellite maps render it as a mottled oval, red and blue speckles scattered across an otherwise uniform orange background, representing temperature variations of only a few hundred thousandths of a degree. That faint, barely perceptible mottling is quite literally a baby picture of the entire universe, taken when it was roughly 380,000 years old. Penzias and Wilson's original antenna, the Homedale horn, remains preserved today as a National Historic Landmark in New Jersey, a strange fate for a piece of hardware originally built for satellite communication and briefly, memorably, home to a family of nesting pigeons. It stands now as a quiet monument to how often genuine discovery arrives disguised as an inconvenience someone was simply trying to fix. It is worth adding a note on precisely why the cosmic microwave background had to appear roughly 380,000 years after the Big Bang specifically, rather than immediately at the very start. Before that point, the extremely hot, dense early universe was filled with an opaque plasma, ionized particles that scattered light constantly, making the universe effectively foggy and impossible to see through. Once the universe cooled enough for electrons and protons to combine into stable neutral atoms, an event physicists call recombination, light was finally free to travel unimpeded, and that first free-flowing light is precisely what Penzias and Wilson detected, stretched by billions of years of subsequent cosmic expansion. It is worth adding, too, that this discovery effectively ended a genuinely open scientific question that had persisted for decades, giving astronomers, for the first time in this entire documentary, direct observational access to conditions from the universe's earliest infancy, rather than indirect inference alone. Nearly everything covered in the chapters still remaining, black holes, dark matter, exoplanets, rests on a foundation this single accidental 1965 discovery helped make solid and confirmed. It is worth closing this chapter by naming exactly how the 1965 discovery reframed every earlier chapter of this documentary retroactively. The tally marks on ancient bone, the Babylonian eclipse tables, Ptolemy's epicycles, Newton's gravity, all of it had been, without anyone fully realizing at the time. The slow accumulation of tools eventually pointed, however indirectly, toward confirming that the universe itself had once been compressed into a single, unimaginably hot and dense point. Every earlier chapter turns out to have been a chapter in the origin story too. It is worth adding a final thought closing out this pivotal chapter. There is something almost poetic about the fact that the most important cosmological discovery of the 20th century was made not in pursuit of cosmology at all, but in the mundane, practical effort to make a communications satellite antenna work properly. The universe's origin story, it turns out, had been quietly broadcasting itself the entire time, indifferent to whether anyone happened to be listening for exactly that signal or simply trying to get rid of an annoying, persistent hiss. It is worth closing this pivotal chapter with a final thought before the documentary moves toward its final act. The universe's origin, once confirmed, did not close the book on cosmology. It opened an entirely new set of questions about what happened in that first fraction of a second, what came before it, if the word before even means anything at that boundary, and what the universe's ultimate fate will eventually be. Confirmation of the beginning, it turns out, was only ever the start of a much longer conversation. Hold on to this image. Two engineers accidentally photographing the afterglow of creation itself while trying to fix a persistent radio hiss as we move forward. The universe's beginning was no longer in question. What remained genuinely, dangerously in question was what its most extreme, most violent objects were actually doing out there in the dark. It is worth closing this pivotal chapter with a final direct thought. Two men trying to eliminate an annoying noise from a satellite antenna ended up handing humanity direct, physical proof of its own origin. There's a lesson worth sitting within that, about how often the most important discoveries arrive disguised as something else entirely, something someone was simply trying to fix. For decades after Schwarzschild's original solution, black holes remained almost entirely theoretical, a strange mathematical prediction with no confirmed real-world example. That began to change in 1971, when astronomers studying a powerful X-ray source in the constellation Cygnus, designated Cygnus X1, found strong evidence of a compact, invisible object with a mass roughly 15 times that of the Sun, orbited by a visible companion star being slowly stripped of its outer layers. Nothing could be seen directly. That was, in a strange way, exactly the point. The evidence for a black hole is almost always indirect. Infer from the gravitational effect on visible matter nearby, the way a companion star gets distorted and stripped, the way X-rays flare from matter being violently heated as it spirals inward before crossing a boundary from which nothing, not even that radiation, can escape. Through the 1970s, 80s, and 90s, evidence accumulated steadily. Astronomers found strong indications of a supermassive black hole, millions of times the mass of the Sun, sitting at the exact center of our own Milky Way galaxy. Tracked by watching stars whip around an invisible point at extraordinary speeds, their orbits only explicable if something with immense, concentrated mass sat there, unseen. In 2015, a different kind of confirmation arrived, validating yet another piece of Einstein's century-old theory. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, directly detected ripples in space-time itself, caused by two black holes, roughly 30 times the mass of the Sun each, spiraling into one another and merging over 1 billion years ago, in a collision so violent it briefly outshone every star in the observable universe combined in gravitational wave energy alone. Then, in April of 2019, came something that had genuinely never existed before. The Event Horizon Telescope, a coordinated network of radio telescopes spanning the entire planet, effectively turning Earth itself into a single telescope the size of the globe, produced the first ever direct image of a black hole silhouette, a supermassive object at the center of the galaxy M87, 55 million light-years away. The image itself is almost anticlimactic to describe. A fuzzy, glowing orange ring, asymmetric, surrounding a dark central void. But that darkness at the center is not an absence of data. It is the event horizon itself, the boundary beyond which light cannot escape, photographed for the first time in human history, rather than merely calculated on paper. And here's where the story stops being simply triumphant and becomes something closer to unsettling. Inside that event horizon, at the exact mathematical center of a black hole, Einstein's equations predict a singularity, a point of theoretically infinite density and zero volume, where the known laws of physics simply cease to produce meaningful answers. This is not a gap that better telescopes will eventually close. It is a genuine, structural failure point in our best current understanding of reality, a place where general relativity and quantum mechanics, our two most successful physical theories, contradict each other so badly that neither one can offer a coherent answer. We have photographed the edge of ignorance itself and confirmed with total certainty that it is real. The mathematical description of a black hole structure was refined significantly beyond Schwarzschild's original, relatively simple, non-rotating case. In 1963, mathematician Roy Kerr found an exact solution describing a rotating black hole, a far more physically realistic scenario, since virtually every massive object in the universe, stars included, rotates to some degree as it collapses. Stephen Hawking's contributions throughout the 1970s pushed the theory even further into strange territory. In 1974, he proposed that black holes are not, in fact, entirely black. Through a quantum mechanical effect, now called Hawking radiation, black holes should very slowly leak energy and, over almost inconceivably long timescales, eventually evaporate entirely, a prediction that remains unconfirmed observationally to this day, since the effect is far too faint to currently detect. The Event Horizon Telescope's 2019 image was itself the product of an extraordinary act of technical coordination, combining data from 8 radio observatories spanning Antarctica, Chile, Hawaii, Arizona, Mexico, and Spain, synchronized using atomic clocks accurate to within a fraction of a second, then processed by a team led by computer scientist Katie Bauman, whose algorithm helped assemble the scattered raw data into a coherent final image. In 2022, the Event Horizon Telescope team released a second image, this time a Sagittarius A star, the supermassive black hole sitting at the exact center of our own Milky Way galaxy, roughly 27,000 light-years from Earth. Producing that image proved even more technically demanding than the earlier M87 result. because gas swirling around our own galaxy's black hole changes on timescales of minutes rather than days, blurring the picture unless corrected for extraordinarily carefully. It is worth explaining precisely why a black hole's interior remains genuinely, structurally unknowable rather than merely difficult to observe. Any information that crosses the event horizon cannot, by definition, send any signal back out. Not light, not radio waves, not any known physical carrier of information. This is not a limitation of current technology that better instruments might eventually overcome. It is a hard boundary built directly into the geometry of space-time itself. This unresolved tension between general relativity, which governs black holes and large-scale gravity, and quantum mechanics, which governs the extremely small, remains one of the most actively pursued open problems in all of physics. Theoretical frameworks like string theory and loop quantum gravity have each attempted to reconcile the two, and neither has yet produced experimentally testable predictions that would settle the question decisively. It is worth adding a clarifying note on precisely how astronomers first inferred a black hole's mass indirectly, well before any direct imaging became possible. By carefully tracking the orbital motion of visible matter, whether a companion star or swirling gas, around an invisible central point, and applying the same essential Newtonian and relativistic mathematics that predicted Neptune's existence over a century earlier, scientists could calculate the mass of the unseen object with real confidence, using gravity itself as the only necessary detection instrument. It is worth adding, too, a note on the astonishing technical scale of the Event Horizon Telescope project as a piece of pure engineering, distinct from the physics it confirmed. Because Earth-based radio telescopes could not be physically connected by cable across such vast intercontinental distances, each observatory recorded data locally onto hard drives, synchronized by hydrogen maser atomic clocks, and the physical hard drives themselves were later flown to a central processing facility, since even modern data networks could not move that volume of raw information fast enough. It is worth closing this chapter by returning, one final time, to how strange it actually is that humanity managed to photograph something explicitly defined by its own invisibility. A black hole, by definition, emits no light of its own. What the Event Horizon Telescope actually captured was the glowing, superheated matter swirling just outside that boundary, silhouetted against the true darkness at the center. We did not photograph the black hole itself. We photograph the exact edge of where our ability to see anything at all finally runs out. It is worth adding a final thought closing this chapter, connecting it forward to what remains. Confirming black holes solved one enormous open question in astrophysics, while simultaneously opening an even larger one, the exact nature of the singularity hidden at their center. That pattern, a hard-won answer immediately generating a deeper, harder question, has now appeared repeatedly across this documentary's entire length, and the two final chapters ahead will show it playing out at the very largest scale the universe has to offer. It is worth closing this chapter with a final thought that bridges directly into the documentary's final two chapters. Black holes taught astronomers something uncomfortable and valuable at once. That direct observational confirmation and complete theoretical understanding are not the same achievement, and reaching one does not guarantee reaching the other. We can now see a black hole's silhouette with our own instruments. We still cannot explain what is actually happening at its very center. Both of those facts are true simultaneously. Hold on to this image, a photograph of the one boundary in the universe where our physics simply stops explaining anything at all as we move forward. That kind of confirmed, photographed ignorance was about to turn out to be far more common across the universe than anyone in this documentary's earlier chapters could have possibly guessed. It is worth closing this chapter with a final, direct thought. We have now photographed the one place in the known universe where our best physics simply gives up and stops offering answers. That is not a failure of this documentary story. It is, arguably, one of its most honest moments, a hard boundary marked clearly rather than papered over with false confidence. It is worth adding, finally, that anyone can now see a version of this image for themselves, freely published online by the Event Horizon Telescope collaboration, a strange kind of democratized access to a discovery that once required an entire global network of instruments and years of processing to produce even once. In the 1970s, an astronomer named Vera Rubin was studying how fast stars orbit around the centers of spiral galaxies. Basic physics, the same physics Newton and Kepler had worked out centuries earlier, predicted that stars farther from a galaxy's center should orbit noticeably slower than stars closer in, the same way outer planets in our solar system move more slowly than Mercury. That is not what Rubin found. Stars far from the center of the galaxies she studied were orbiting almost as fast as stars near the center, far faster than the visible matter in those galaxies should have been able to gravitationally hold in place. By all visible accounting, these galaxies should have been flying apart. They were not flying apart, which meant something was holding them together, something with real gravitational mass, that was not showing up in any telescope at any wavelength visible light, radio, infrared, X-ray, nothing. Rubin's careful, repeated measurements across dozens of galaxies made the pattern impossible to dismiss as an error. Astronomers named this invisible, undetected mass dark matter, and the name is, frankly, a small act of scientific honesty disguised as a label. It does not mean we know what it is. It means we know something is there gravitationally, and we cannot currently detect it directly by any means available to us. Current estimates suggest dark matter makes up roughly 27% of the entire universe. Ordinary matter, everything ever studied throughout this entire documentary, every star, every planet, every human being who ever built a telescope, accounts for only around 5%. The rest, the majority, sits entirely outside our direct observational reach. Then, in 1998, two independent teams of astronomers, studying distant exploding stars called Type Ia supernovae to measure how the universe's expansion rate had changed over billions of years, found something nobody had predicted or particularly wanted to find. The expansion of the universe was not slowing down under its own gravity, as almost everyone had assumed it must be. It was accelerating. Something was actively pushing the universe apart, faster and faster, working directly against gravity on the largest scales. Astronomers named this mysterious force dark energy, and it turns out to be, by far, the largest single component of the entire universe, making up roughly 68% of everything that exists. Add it up honestly, and the conclusion is almost embarrassing after everything astronomy has accomplished across this entire story. Roughly 95% of the universe is made of something we cannot see, cannot directly detect, and genuinely do not understand. All of human astronomy, from bone tally marks to the Event Horizon Telescope, has spent its entire history studying the smaller, easier 5%. This is astronomy's most humbling admission, and it is worth resisting the urge to treat it as a failure. Every increase in precision, every improved telescope, every refined measurement has not brought us closer to a final, tidy answer. It has revealed a larger, unknown hiding just beneath the one we thought we had solved. That pattern, if you have been paying attention, should feel very familiar by now. Fritz Zwicky, a Swiss astronomer working in California decades before Vera Rubin's confirming work, had actually proposed something remarkably similar to dark matter as early as 1933, studying the motion of galaxies within the Coma Galaxy cluster and finding they moved far too quickly to be held together by the visible mass alone. Zwicky, notoriously abrasive and frequently dismissed by his contemporaries, called the missing mass Dunkel Materie, dark matter, in German, decades before the idea gained mainstream acceptance. Zwicky's reputation for abrasiveness likely cost his idea decades of serious consideration. He reportedly referred to colleagues who disagreed with him as spherical bastards, explaining that they were bastards no matter which direction you looked at them from. It took Vera Rubin's far more measured, methodical, and repeatedly confirmed observations, nearly 40 years later, to finally push dark matter from a fringe suggestion into a mainstream scientific problem demanding serious attention. The 2011 Nobel Prize in Physics went to Saul Perlmutter, Brian Schmidt, and Adam Rees, the leaders of the two independent supernova research teams whose 1998 findings first revealed the accelerating expansion of the universe. Both teams had actually set out expecting to confirm that the expansion was slowing down, planning to measure exactly how much gravity was decelerating it. Both teams found, to their own initial disbelief, the precise opposite result. Current experiments attempting to directly detect dark matter particles, buried deep underground in old mines to shield against interference from ordinary cosmic radiation, have so far come back empty across decades of increasingly sensitive searches. That persistent, expensive silence is itself meaningful data, steadily ruling out entire categories of theoretical particles and narrowing, slowly and expensively, what dark matter is still allowed to be. The Bullet Cluster, a pair of colliding galaxy clusters roughly 3.7 billion light-years away, provided one of the most visually direct pieces of evidence for dark matter's existence when it was analyzed in detail in 2006. Gravitational lensing maps showed the majority of each cluster's mass had separated from its visible, ordinary matter during the collision, exactly as expected if that mass were made of a different, largely non-interacting substance, moving mostly unaffected through the cosmic wreckage. It is worth being honest about how strange the term dark energy actually is, scientifically speaking, compared to dark matter. Dark matter, whatever it turns out to be, at least behaves like ordinary matter gravitationally, simply invisible to light. Dark energy behaves nothing like anything else in physics, a property of empty space itself that pushes outward rather than pulling inward, and its true nature remains, arguably, the single largest unresolved mystery in the entirety of modern cosmology. It is worth adding a note on precisely how astronomers now use the cosmic microwave background itself, discussed several chapters earlier, as an additional independent line of evidence for both dark matter and dark energy. The precise pattern of those tiny temperature ripples across the sky depends sensitively on exactly how much ordinary matter, dark matter, and dark energy the universe contains, and current best-fit models require almost exactly the same proportions, roughly 5% ordinary matter, 27% dark matter, 68% dark energy. That galaxy rotation curves and supernova measurements had already independently suggested. It is worth adding, finally, a note of genuine scientific humility that runs underneath this entire chapter. Multiple, completely independent lines of evidence, galaxy rotation, gravitational lensing, supernova brightness, and the cosmic microwave background, all converge on roughly the same numbers for what the universe is made of, even though none of these methods can yet say precisely what dark matter or dark energy actually are at a fundamental physical level. Confidence in the measurement and confidence in the underlying explanation this documentary keeps discovering are simply not the same thing. It is worth closing this chapter with a genuinely uncomfortable thought that this documentary has been building toward across nearly its entire length. Every prior expansion of astronomical knowledge, from a single Earth to a solar system, from a solar system to a galaxy, from a galaxy to billions of galaxies, eventually got absorbed, understood, and folded into an increasingly confident picture of reality. Dark matter and dark energy have resisted that absorption for decades now. It remains entirely possible that this particular mystery does not resolve within the lifetime of anyone currently watching this documentary. It is worth adding a final thought closing this chapter directly. There is a specific kind of intellectual honesty required to spend an entire scientific career building increasingly precise instruments, only to have those instruments reveal that the vast majority of the universe remains entirely outside your ability to directly detect. Astronomy did not fail by discovering dark matter and dark energy. It succeeded exactly as it was supposed to, by getting precise enough to notice, honestly and clearly, exactly how much remains genuinely unknown. It is worth closing this chapter with a final thought that sets up the documentary's true final argument. If 95% of the universe remains genuinely unexplained despite our best current instruments, then every previous chapter of confident discovery in this documentary needs to be understood correctly, not as a series of final answers, but as a series of thresholds, each one revealing a little more of a darkness that had been there unnoticed the entire time. Hold on to this image. 95% of everything that exists sitting entirely outside our direct ability to detect it as we move toward this documentary's final chapters. Even with that much of reality still hidden, astronomers kept finding new tools, and those tools were about to start finding entire other worlds orbiting other suns scattered across our own galaxy. It is worth closing this chapter with a final direct thought before the documentary's true argument arrives. Every single previous chapter in this story ended with more known than before began. This one, honestly, ends with less certainty than the chapter before it, even though the instruments involved were considerably more advanced. That reversal is worth sitting with carefully before we move any further. For most of astronomy's history, the question of whether planets existed around other stars was pure speculation, philosophically interesting, but observationally hopeless. Other stars are so distant and so much brighter than any orbiting planet that directly seeing a planet next to its star is, in most cases, still functionally impossible with current instruments. Astronomers found a workaround. A planet orbiting a star exerts a small gravitational tug on that star, causing it to wobble slightly, which shows up as a tiny, rhythmic shift in the star's light spectrum. This is the radial velocity method, and in 1995, astronomers Michel Mayor and Didier Queloz used it to confirm the first planet ever detected orbiting a sun-like star, 51 Pegasi b. A second method proved even more powerful for finding planets in bulk. If a planet's orbit happens to pass directly between its star and Earth, it blocks a tiny, measurable fraction of that star's light on a regular, repeating schedule. NASA's Kepler Space Telescope, launched in 2009, used exactly this transit method, staring continuously at over 150,000 stars, watching for that faint, periodic dimming. The results reshaped how astronomers think about our galaxy entirely. Kepler alone confirmed thousands of exoplanets before its mission ended in 2018, and statistical extrapolation from its data suggests the Milky Way likely contains more planets than stars. Its successor, the Transiting Exoplanet Survey satellite, TESS, launched in 2018, continues the search across the entire sky rather than a single fixed patch. Meanwhile, the 2015 detection of gravitational waves by LIGO, first confirmed in that black hole merger discussed earlier, opened an entirely new observational channel that had never existed before. Astronomy, for its entire history, had relied on light, in one form or another, to study the universe. Gravitational waves let scientists, for the first time, listen to the universe through an entirely different physical phenomenon altogether. In December of 2021, after decades of development and delay, the James Webb Space Telescope launched, eventually settling into an orbit around a gravitationally stable point roughly 1 million miles from Earth. Its instruments are tuned primarily to infrared light, which lets it see through obscuring dust clouds and, critically, detect the extremely stretched, redshifted light from the earliest galaxies that ever formed. Because light takes time to travel, looking farther away is functionally the same as looking further back in time. Webb has captured light from galaxies that formed only a few 100 million years after the Big Bang itself, showing astronomers, more or less directly, what the infant universe actually looked like, something no instrument before it had ever been capable of resolving. The pace of all of this, taken together, is genuinely dizzying compared to almost everything that came before it in this story. Babylonian astronomers spent 7 centuries accumulating one continuous data set. Webb produces observations that would have been considered impossible even by working astronomers in the 1990s, on an operational timescale measured in weeks rather than centuries. And yet, even now, with more data flowing in than at any point in this entire 5,000-year story, the fundamental mysteries have not gotten smaller. What dark matter actually is remains unknown. What dark energy actually is remains unknown. What happens inside a black hole's singularity remains, quite possibly, permanently unknowable given our current physics. The instruments keep getting better. The unanswered questions keep getting bigger right alongside them. The confirmation of gravitational waves in 2015 traced back to a prediction Einstein himself had made a full century earlier, in 1916, as a consequence of general relativity, though Einstein privately doubted for years whether the effect would ever be strong enough to actually detect. LIGO's instruments had to measure a distortion in space-time smaller than 1/10,000th the width of a proton, an almost unimaginable degree of sensitivity, to catch the signal from that distant black hole merger. The James Webb Space Telescope's development history was itself a decades-long saga of delay and near cancellation, originally proposed in the 1990s under a different name, facing repeated budget overruns that at one point threatened the entire project in the United States Congress. It launched, finally, more than 14 years behind its original planned schedule and many times over its original projected cost. Within its first year of operation, Webb had already begun overturning assumptions that had held for decades. It found galaxies in the extremely early universe that appeared unexpectedly massive and structured for their age, a finding that some astronomers described, only half-joking, as breaking cosmology, and that remains an active, unresolved puzzle at the time of this recording. Among the thousands of confirmed exoplanets, a small number sit in what astronomers call the habitable zone, the narrow orbital range around a star where liquid water could plausibly exist on a rocky surface. None of these candidates has yet been confirmed to actually host life, and confirming it, given the distances involved, may remain functionally impossible for a very long time, even as the list of promising candidates keeps growing. The scale of modern exoplanet discovery is worth stating plainly, because the number itself has become almost too large to intuitively grasp. As of the mid-2020s, astronomers have confirmed over 5,000 exoplanets, with thousands more candidates awaiting confirmation, discovered across barely 3 decades of dedicated searching, compared to the entire multi-thousand-year span this documentary has otherwise covered for everything else in the solar system. Beyond simply detecting planets, newer instruments have begun directly analyzing exoplanet atmospheres, using starlight filtered through a planet's air as it passes in front of its star, revealing traces of water vapor, carbon dioxide, and other molecules on worlds many light years away. It is a technique that would have sounded like pure fantasy to Herschel or even to Hubble, and it is now, quietly, becoming routine. It is worth adding a note on precisely why detecting an exoplanet's atmosphere is so much more technically demanding than simply detecting the planet's existence in the first place. The signal involved, the tiny dip in starlight at specific wavelengths as it filters through a distant planet's thin atmospheric layer during a transit, is almost unimaginably faint, often representing a change of only a few parts per million in the star's overall brightness, requiring instruments of extraordinary sensitivity and painstaking statistical analysis across many repeated transits to confirm. It is worth adding, too, a note on how the 2015 gravitational wave detection connected directly back to Einstein's original, largely theoretical 1916 prediction, closing a scientific loop that had remained genuinely open for almost exactly 1 century. Very few scientific predictions in history have waited a full 100 years for direct experimental confirmation, and the fact that this one arrived almost precisely on that century mark gave the discovery an unusually poetic resonance within the physics community itself. It is worth closing this chapter by naming the strange emotional texture of living through an era of accelerating discovery, something none of the earlier astronomers covered in this documentary ever experienced. Kepler waited years between individual insights. Modern astronomers, working with instruments like TESS and James Webb, receive new, potentially paradigm-shifting data on a rolling, near-constant basis. The sheer pace of incoming information has become, in its own right, one of the defining and disorienting features of astronomy's current moment. It is worth adding a final thought closing this chapter before the documentary's final act. Every tool covered here, transit photometry, radial velocity, gravitational wave interferometry, infrared deep field imaging, exists because of a direct, traceable lineage running all the way back to Galileo's first crude telescope and Newton's first equations of motion. Nothing in modern astronomy arrived from nowhere. Every current instrument is simply the latest, most refined link in a chain this entire documentary has been tracing from the very beginning. It is worth closing this chapter with a final thought heading into the documentary's true ending. The tools have never been better. The pace of discovery has never been faster, and the list of confirmed unknowns has, if anything, only grown longer alongside all of it. That is not a contradiction. It is, as the final chapter is about to argue directly, the single most consistent pattern running through the entire history you have just spent hours listening to. Hold on to this image. Discovery accelerating faster than at any previous point in this entire 5,000-year story. As we move toward the very last chapter, every single new tool covered in this chapter has done exactly what every previous tool in this documentary has also done. It has answered old questions, and it has opened new ones faster than anyone can properly close them. It is worth closing this chapter with a final, direct thought before this documentary's true ending. Every single tool covered across this entire runtime, from a notched bone to a space telescope orbiting 1,000,000 miles from Earth, has done exactly one consistent thing throughout this entire 5,000-year story. It has revealed more than it settled, every single time, without exception. It is worth adding, before we close, that some of these newer instruments are already being planned as successors before their predecessors have even finished their primary missions, a pace of institutional planning that would have seemed almost unimaginable to any astronomer covered earlier in this documentary. Go back for a moment to where we started this whole story. A grain of sand held at arm's length, a patch of sky that looked completely empty, revealing thousands of galaxies once someone was patient enough to actually look. That image was never really the ending of anything. It was simply the most recent threshold in a pattern that has been repeating for as long as anyone has bothered to count. Consider how many times that exact pattern has already played out across everything covered in this documentary. A person scratches lunar marks onto a bone, and the sky becomes trackable rather than random. Babylonian scribes turn that tracking into 7 centuries of prediction, and the sky becomes mathematical rather than mysterious. Ptolemy builds an elegant, working model, and it takes 1,400 years for anyone to prove it was fundamentally wrong. Copernicus quietly moves the Earth out of the center. Kepler bends the planets' paths into ellipses. Newton binds heaven and Earth under one single law. Herschel doubles the size of the known solar system in a single night, almost by accident. Each one of these people believed, at least for a while, that they had found something close to a final answer. Every single one of them was wrong about that specific part. Hubble proves the Milky Way is not the entire universe, and the universe instantly becomes almost incomprehensibly larger than anyone had assumed. Penzias and Wilson stumble onto the leftover heat of the Big Bang, and the universe suddenly has a confirmed, measurable beginning. Rubin measures galaxy rotation, and it turns out almost everything in the universe is made of something we still cannot see or name. Notice the shape of that pattern, because it is the actual argument this entire documentary has been quietly building toward. Every single major breakthrough in the history of astronomy did not close a mystery. It opened a bigger one directly underneath the one it had just solved. Geocentrism gives way to heliocentrism. A single galaxy gives way to billions of galaxies. Ordinary matter gives way to dark matter and dark energy. 95% of reality that remains, for now, functionally invisible to us. There is no honest reason to believe that pattern is finished. No reason to believe James Webb's images of the infant universe, or the still unexplained nature of dark energy, or the singularity sitting silently at the center of every black hole, represents some kind of final chapter. Every previous generation of astronomers believed, at some point, that they were close to a complete picture. Every single one of them was standing at a threshold they mistook for a summit. We are almost certainly doing the same thing right now, with our own confident language about the composition of the universe, our own current physics, our own sense of how much we have finally figured out. It is a strange, quietly unsettling thought to end on, and it is, as far as anyone can currently tell, simply true. So return, one final time, to that grain of sand held at arm's length. Thousands of galaxies packed into what had looked, to the naked eye, like absolutely nothing. It was never the answer this documentary opened with. Understood correctly, it was always just the doorway. And on the other side of it, unmeasured, unnamed, and almost certainly still there right now, waiting, is whatever comes next. It is worth stating plainly, one final time, exactly how short this entire recorded story actually is, set against the scale it describes. Roughly 43,000 years since the Lubombo bone. Roughly 6,000 years of organized, written astronomical record-keeping. A little over 400 years since Galileo first pointed a telescope upward. The universe itself, by current measurement, is approximately 13.8 billion years old. Set against that number, the entire span of this documentary, every chapter, every named astronomer, every hard-won correction to an earlier mistaken model, occupies a sliver of time so thin it barely registers as a rounding error. And yet within that sliver, a species without wings, without any direct way to leave its own planet for most of that history, worked out the shape, the age, and something close to the composition of the entire observable universe. That is not a small thing. Even sitting alongside everything this documentary has also had to admit we still do not know. Ignorance and achievement, it turns out, are not opposites. They grow together, each one making the other more visible. The way a lit room only reveals how large the darkness around it actually is. Whatever comes next in this story, whoever is watching centuries from now, if anyone is, will very likely look back at our current confident language about dark matter, dark energy, and singularities the exact same way we now look back at Ptolemy's epicycles. Not with contempt, with recognition. The best possible attempt, made with the tools available at the time, by people who genuinely believed they were closer to the answer than they actually were. There is one more detail worth leaving you with before this documentary ends. The atoms in your own body, the calcium in your bones, the iron in your blood, were forged inside the collapsing cores of stars that died and scattered their contents across space long before our own sun ever formed. The history we have just spent hours tracing is not only a history of instruments and equations. It is, in a very literal sense, also your own. It is worth naming, one final time, exactly why this pattern of expanding ignorance should not be read as a story of failure, despite how it might initially feel. Every single expansion of mystery in this documentary followed directly from a genuine, hard-won expansion of knowledge. We did not discover dark matter and dark energy because our instruments got worse. We discovered them because our instruments and our mathematics finally became precise enough to notice something had been quietly missing the entire time. There's a version of this story that ends in despair, the endless regress of unanswered questions treated as proof that certainty is permanently out of reach. There is another version closer to what this documentary actually believes, where that same regress is treated as the entire reason to keep looking, not despite the fact that every answer breeds a bigger question. Because of it, it is worth adding a final, direct comparison that ties this entire closing argument together concretely. The Babylonian astronomers who tracked eclipses across 7 centuries never lived to see Ptolemy's model, let alone its eventual overthrow. Ptolemy never lived to see Copernicus quietly move the Earth off-center. Copernicus never lived to see Galileo confirm it through a telescope. Every single astronomer in this documentary handed an unfinished project forward to people they would never meet, trusting a pattern of inquiry larger than any individual life could contain. It is worth ending, honestly, on the fact that this documentary itself is part of exactly that same unfinished handoff. Everything stated here with confidence, the age of the universe, the proportions of dark matter and dark energy, the physics breaking down inside a black hole singularity, will very likely be refined, corrected, or entirely reframed by discoveries neither this documentary nor the people who made it can currently anticipate. That is not a weakness in the story. Judging by every single chapter that came before this one, it is simply how the story has always worked. It is worth closing this entire documentary with a direct, quiet acknowledgement of what has actually just happened across the last several hours. You have moved through roughly 43,000 years of human attention paid to the night sky, from a single anonymous person marking a bone by firelight to a coordinated global network of telescopes photographing the edge of a black hole. Somewhere in that compressed journey, the skies stopped being simply something overhead and became, instead, the single longest-running conversation our species has ever managed to sustain with itself. It is worth adding one truly final thought before this documentary ends completely. Somewhere, right now, tonight, an instrument somewhere on Earth or in orbit above, it is collecting data that will, within a few years, quietly overturn some confident claim made earlier in this very documentary. That is not a flaw to apologize for. It is the entire mechanism by which any of this knowledge was ever built in the first place. And it is, if you have been paying attention this whole time, the closest thing to a genuine promise this story has to offer. There is one true final image worth leaving you with, separate from the Hubble Deep Field itself. Somewhere, tonight, a person with no telescope at all is simply standing outside, looking up, the exact same basic act performed by someone 43,000 years ago with a bone and a blade. The instruments have changed almost beyond recognition. The impulse underneath them, the refusal to look away from what is genuinely unknown, has not changed even slightly. And if this documentary has argued anything at all, it is that this impulse is very unlikely to stop now. Thank you for staying with this story all the way through, from a single notch bone in the dark to a photograph of the one place in the universe where physics itself simply stops. Whatever you look up and see tonight, however ordinary it might seem, it is very likely doing exactly what it has always done throughout every chapter of this documentary, holding far more than it first appears to. Sleep well, if that is why you came. And if you're still awake, look up before you close your eyes tonight. It is worth it.